to answer the questions. All of you are going to answer some questions. So this is your enzymology, general concepts, and enzyme kinetics. The lecture is divided into two parts, the general concepts and enzyme kinetics. Of course, in between, we shall have a probably a 10-minute break. So, can you see the first slide? Kita nyo ba?
Yes po, Doc, kita po.
All right, sige. Okay, this is it. I'll give you a some cool facts about enzymes. Enzymes utilize sidekick or cofactors to function. In other words, they need cofactors. Of course, not all enzymes need cofactors, no, but most of them need cofactors. Some of these factors are monogamous, others are polygamous or promiscuous. No, so these are somewhat cool facts about enzymes. Some enzymes have suicidal characteristics. Okay, enzymes can be extremes. One enzyme allows a reaction to take place in milliseconds that would otherwise take every 78 million years to occur. Inhibition of some enzymes are used to treat clinical disorders. Right? So this is our first clinical scenario. I'm sure you have a copy of my PowerPoint. You have it? Ha? Meron kayo?
Yes po, Doc.
Okay. In March 30, this is a actual event, no? In March 30, 1995, the Om Shinrikyo terrorist group undertake 5 coordinated release of sarin gas at the peak of the morning rush hour on several subway commuter train lines of Tokyo Metro. 13 persons were killed, 50 severely injured, and 1,000 others developed temporary vision problems. 189 members of the terrorist religious group were indicted. 13 were sentenced to death, 5 were given life imprisonment, 80 were given prison sentences of varying length, 87 received suspended sentences, 12 were fined, and 1 was found not guilty. All right, this is the second clinical scenario. A 50-year-old male, obese and hypertensive, consulted because of extreme tenderness and swelling of the right big toe associated with limping gait. History revealed moderate alcohol intake of 10 years. He is fond of eating shellfish and organ meats during drinking session with friends. His blood uric acid level was elevated. He was given allopurinol and was advised drastic lifestyle modification. All right. The first scenario, these are images in the aftermath of simultaneous sarin gas attacks in several subway trains in Metro Tokyo, showing quite a number of victims with various autonomic nervous system manifestations, which can lead to death. No? Now, sarin gas inhibits the enzyme acetylcholinesterase that is supposed to degrade acetylcholine, the neuromuscular the transmitter in the neuromuscular junction, resulting to increase in level of acetylcholine, hence the clinical manifestations. So here we encounter an enzyme that is manipulated to wreak havoc on humanity. The second clinical scenario is simply gouty arthritis. So this is a picture of a tender, swollen, painful inflammation secondary to gouty arthritis of the right big toe of an alcoholic. Patient was given allopurinol, a drug that inhibits the synthesis of uric acid from certain precursors. Here, an enzyme is manipulated to restore well being in humanity. So, you have two clinical scenarios that introduces to how enzymes work. All right. One against humanity, another one is for humanity. So, for this lecture, this will be our learning objectives. Here, define the following enzymes: apoenzyme, coenzyme, holoenzyme, metalloenzyme, rotatory enzyme, active side of the enzyme, allostatic side of the enzyme, substrate. There. Discuss the helper or cofactors of enzymes. Enumerate the six major classes of enzymes. Discuss the characteristics of enzymes. Compare the two models of enzyme substrate complex. Describe the operation and plots used to illustrate enzyme kinetics. You have your Michaelis Menten saturation curve. You have your Lineweaver-Burke double reciprocal plot. You have Michaelis constant and its significance, and of course, kinetic order of reactions. Differentiate the major type of enzyme inhibition from the standpoint of enzyme kinetics. You have reversible and irreversible inhibition. Number 8, elucidate the different ways of regulating enzyme activity. Number 9, explain the factors affecting enzyme activity. Number 10, elucidate the therapeutic uses of enzyme inhibitors. Discuss diagnostic utility of some clinical enzyme assays. All right. So, okay. Definition. What are enzymes? Enzymes are specialized protein catalysts that accelerate chemical reactions in biologic systems to about 10 to the 6 to 10 to 20 times faster than uncatalyzed reactions, but are not consumed or used up during the reaction they catalyze. In other words, at the end of the reaction, the enzymes are regenerated for reuse or reutilization. So there is no net consumption of your enzymes. Some enzymes make their conversion of substrate to product to product, to product that occur many million years, millimillion of times faster. And this is an extreme example of an enzyme. You don't have to memorize this. This is an enzyme, orosdelic acid decarboxylase, an enzyme involved in pyrimidine synthesis, which allows a reaction in milliseconds that would otherwise take every 7 to 8 million years to occur. In this reaction, OMP or orethidine monophosphate is decarboxylated, remove or carbon dioxide to UMP, uridine monophosphate uridylate, all right, which is a precursor of RNA, and RNA is found in genes. So this is an extreme example of an enzyme. Next, definition of terms. There, sorry. An apoenzyme refers to the protein part of an enzyme without any cofactors or prosthetic groups. It gives the enzyme the necessary three-dimensional infrastructure for clinical chemical reaction. It is catalytically inactive and heat labile. All right. Now, cofactors, collective term that refers to the small soluble non-protein component required for apoenzyme activity. They are reversibly bound to the enzyme. Like enzymes, they are not changed or modified during catalysis but are regenerated. There are three groups. You have three groups of your cofactors. You have your coenzyme, you have your prosthetic group, and the metal ion. Coenzymes, these are small organic molecules often derived from your B complex vitamins, no? And other water soluble vitamins bound covalently or loosely to the apoenzyme, hence released from the enzyme's active site during the reaction to bind again to another enzyme molecule. These are also called co-substrates. These are promiscuous or polygamous since they associate with the enzyme only for the purpose of the reaction and then diffuse away for the next liaison with another. That would be your coenzyme. Your prosthetic group, these are small organic molecules firmly or tightly or permanently attached to the apoenzyme during the entire catalytic activity. They are monogamous since they are permanently bonded to the active site of the enzyme and stay with the enzyme after completion of your reaction. Example of this would be your biotin, your FAD or flavin, adenine, dinucleotide, your pyridoxal phosphate, your thiamine pyrophosphate, and your lipoic acid. No? The third would be your metal ions and iron sulfur clusters. These are inorganic molecules utilized by some enzymes and involved in electron transfer reaction. They are tightly bound to the active site of the enzyme, hence, these are monogamous in nature. All right. Now, sorry. The holoenzyme, therefore, would be apoenzyme plus your cofactor. This is the fully or completely catalytically active enzyme. That would be your holoenzyme. Any questions so far? No question. Okay, no question. All right. There are several ways of classifying your enzymes. You have your activation transfer coenzymes, exemplified by your TPP, your coenzyme A, biotin, and your pyridoxal phosphate. And the second would be your oxidation reduction coenzyme. In other words, they are involved in dehydrogenation reactions, your NAD+, FAD, vitamin E, and vitamin C. All right. Okay. This is the first question. Which of the following is the catalytically active coenzyme? Letter A, letter B, letter C, letter D. Let me see. Abraham, Chelsea. Chelsea Abraham, are you here?
Yes po, Doc. Hello po.
Yes, what's your
Good
answer
morning.
here?
Good morning po. My answer po is C, holoenzyme.
Okay, that's correct. So holoenzyme is the catalytically active. It is made up of your cofactor and then your coenzyme. All right, thank you. All right, these are enzyme cofactors, your coenzyme or organic molecules. Usually, but not always, derived or synthesized from your B complex vitamins. These are your B complex vitamins. In other words, those are vitamins and act as transient carriers of specific functional groups. In other words, they carry functional groups from one enzyme to another enzyme. All right. Now, in vitamins, let me just start the discussion. Vitamins, to be metabolically useful to man, must be converted first to their coenzyme form before they can participate in any chemical reactions. No, they have very little activity and specificity in the absence of an enzyme. Again, these are generally loosely bound to the enzyme, hence continuously regenerated, and their concentrations maintained at a steady level in the cell. Hence, small amounts of coenzymes can be used extensively. Mhm. This table shows you a number of vitamins and their coenzyme form, as well as the chemical group transferred. So vitamin B, your thiamine, the coenzyme form would be your thiamine pyrophos. In other words, the body doesn't use vitamin B per se or thiamine per se, but it must be converted to a coenzyme form. In other words, coenzyme for this group of enzymes. And they transfer chemical groups like your aldehydes or hydroxyethyl. Okay. Your thiamine pyrophosphate is a prosthetic group. In other words, it is permanently bound to your enzyme or your apoenzyme. Okay. Your riboflavin or vitamin B2, the coenzyme form is your flavin adenine dinucleotide. And this is the coenzyme of this group of enzymes. They transfer electrons in it, and therefore these are involved in oxidation reduction reactions. FAD is a prosthetic group of these enzymes. In other words, this is permanently bound to your enzyme. Okay. Your nicotinic acid or niacin or vitamin B3, the coenzyme form is your nicotinamide adenine dinucleotide. And this is a coenzyme of a lot of your dehydrogenases. They transfer hydride ion. Hmm? This is a negatively charged hydrogen ion. All right. It is a coenzyme and therefore it is not permanently bound to the enzyme. Okay. This is peridoxine or vitamin B6. The coenzyme form is peridoxal phosphate, which is a coenzyme of this group of enzymes. They are transient carriers of amino groups, especially in transamination reactions. Again, just like your TPP, your PLP is permanently bound to the enzyme. And therefore, these are prosthetic groups of your enzyme. Down the line here, no? Okay. Question. Which of the following is the vitamin precursor of your NAD8? Charlemagne Arias. Is it letter A, letter B, letter C, letter D?
Thiamine po, Doc.
What?
Thiamine po, Doc.
Thiamine?
Uh,
What about Avila? Do you agree with Sharla? He
Hello po,
says
Doc. Good
thiamine.
morning.
Ah,
My answer po is letter A,
okay.
niacin.
It will be niacin, all right? Nicotinamide adenine dinucleotide is derived from your vitamin niacin. All right? Okay, sige. All right, these are other coenzymes. Your pantothenic acid there, the coenzyme form would be your coenzyme A. All right. Next, you'd be your vitamin biotin. The coenzyme form would be your biocytin. It is a coenzyme of your carboxylases. These are all carboxylases, no? They're carriers of carbon dioxide. In other words, these are sources of carbon dioxide in reactions that require the transfer of carbon dioxide. All right, biocytin is permanently bound to your coenzyme. And the rest here, no? Your cobalamin, the coenzyme form is 5' deoxycobalamin. All right. And what else? Folic acid, the coenzyme form will be your tetrahydrofolic acid. These are involved in one carbon transfer in the form of formyl, methanol, or methyl groups. All right. So your tetrahydrofolate abbreviation would be either FH4 or your TH4. These are one and the same. So these are all the coenzyme forms of your vitamins, and most of these are your water soluble vitamins. Okay, I'll give a rundown of your coenzyme. Your coenzyme A here, it is derived from your pantothenic. This is pantothenic acid. No? It is a coenzyme or cofactor of several enzymes like your acetyl-CoA. All right. The active component of your coenzyme A is a sulfide group here that forms thioesters with acyl groups like acetyl, succinyl, or fatty acyl CoA or fatty acyl. All right. So this is an example of a reaction that utilizes your coenzyme A here. This is one of the reactions in your Krebs cycle. Here, take note that alpha ketoglutarate here is oxidatively decarboxylated into succinyl-CoA. This part of your alpha ketoglutarate is released as carbon dioxide. Alpha ketoglutarate is a 5-carbon compound. If you remove one carbon as carbon dioxide, you have a 4-carbon succinyl-CoA. All right? In the presence of your coenzymes, catalyzed by your alpha ketoglutarate dehydrogenase complex. It is a complex because it consists of 5 coenzymes and 3 enzymes. Each of these coenzymes have a certain role to play in the overall reaction process. Okay, that is coenzyme A. It is a cofactor of your alpha ketoglutarate dehydrogenase complex. Okay, next, another reaction, another reaction. When coenzyme A is a cofactor, your pyruvate, it's a 3-carbon here. It is oxidatively decarboxylated into acetyl-CoA at 2-carbon, primarily because the carboxyl group here is released as carbon dioxide. In the presence of, in the presence of your complex, it is a complex because it is made up of several coenzymes and enzymes here. And one of these coenzymes would be your coenzyme A here. All right? Each of these coenzymes and enzymes have certain role to play in the overall reaction process. This is one of the reactions that links your glycolytic pathway with your citric acid cycle, catalyzed by pyruvate dehydrogenase complex. All right. Now, let's take up your nicotinamide adenine dinucleotide here and nicotinamide adenine dinucleotide phosphate. Okay. This is the structure of your nicotinamide adenine dinucleotide. Meron siyang nicotinamide ring, all right, from your niacin. Take a look at the carbon atoms, no? 1, 2, 3, 4, 5, 6. At position number 1, there is a positively charged nitrogen ion. Can you see this red here? Opposite, opposite a carbon ion here at carbon atom at position number 4. All right. By virtue of this, your carbon atom here can accept a negatively charged hydrogen atom. We call this as hydride ion from carbon number 2 of your lactate. All right. So this one accepts your hydrogen atom here there. And this is catalyzed by lactate dehydrogenase. In the process, your lactate here, in the process, your lactate is oxidized into pyruvate. All right? Into pyruvate. Your NAD plus ngayon is reduced to NAD8, NAD8. Okay. Remember, in oxidation, oxidation means removal of your hydride ion, of a hydrogen ion that contains electrons. Reduction would be addition of hydrogen ions. If you remove a hydrogen ion from lactate and the acceptor would be NAD here, your NAD plus will become NAD H and your lactate will be reduced. I'm sorry, I'm sorry, let me repeat. Your NAD plus here is reduced to NAD H. It has an additional hydrogen atom. While your lactate, you remove a hydrogen atom, it is oxidized to pyruvate. All right? So this is lactate dehydrogenase in the presence of NAD plus as a hydrogen acceptor from carbon number 2 of your lactate. And in the process, all right, your NAD plus is reduced to NAD H. Okay. Now in NAD P plus, this is almost the same, NAD P plus, except that this one contains a hydroxyl group, your 2' hydroxyl group. All right, so that would be for NAD plus and NAD P. The plus there in NAD plus, nicotinamide adenine dinucleotide plus, is because of this positively charged nitrogen atom at position 1. All right? Okay. Okay, I'll give an example. This is just the same example as I showed you. So this is lactate. Lactate yan ha. Take a look at there is a negatively charged hydride ion at carbon number 2. In the presence of the hydrogenase here, all right, the carbon atom opposite the positively charged nitrogen atom at position 1 of your nicotinamide ring accepts the hydrogen atom here, and in the process it is reduced to NADH while your lactate is oxidized into pyruvate. Okay. The mnemonic devices is loss of electrons is oxidation. Gain in electrons would be reduction. Did you get that? Gets nyo? Okay. That would be your NAD plus. Next, your biotin, it is a coenzyme of your carboxylases. It is a permanently bound. Okay, it is a prosthetic group. In other words, permanently bound to your carboxylases. Remember, enzymes are made up of a number of amino acids. And one of these amino acids would be your lysine. Okay, it is the lysine residue of an enzyme, carboxylase, that contains a permanently bound biotin. Itong structure ng biotin. And what is important in biotin is there is a nitrogen atom here. Ito. And what is this nitrogen atom? This is the reactive nitrogen group that is the site of attachment of carbon dioxide. All right? That is sort of carbon. So when we talk about biotin, you always think about it is the carrier of carbon dioxide in carboxylation reactions. Okay. Primarily because meron siyang nitrogen atom here. That would be your biotin as a cofactor of your carboxylases enzymes. Clear? Okay, let me proceed further. This is a reaction showing you your biotin as a coenzyme of your pyruvate carboxylase. No? This is the first step in gluconeogenic. Gluconeogenesis refers to the synthesis of glucose from non-carbohydrate substrates when there is decreased level of glucose, as in late fasting. Okay. In this reaction, pyruvate here is carboxylated into oxaloacetate in the presence of biotin because it is a carrier of carbon dioxide. All right, this is the carboxyl group of oxaloacetate that comes from your carbon dioxide, which is carried by your biotin. And therefore, pyruvate, a three-carbon compound, is converted into oxaloacetate, a four-carbon compound, because of the additional carbon dioxide coming from your biotin, catalyzed by your carboxylase. Clear? Any questions so far? No question? Mabilis ba ako? Tama lang? Ha?
Sakto lang po, Doc.
Sakto lang. Okay. Thank you. Another example of carboxylation reaction. Carboxylation of acetyl-CoA to malonyl-CoA. This is one of the steps. This is the rate-limiting step in de novo synthesis of fatty acid. At this point, please don't memorize this reaction. I'm just giving you examples of the functions of your coenzymes. No? Here, acetyl-CoA is carboxylated into malonyl-CoA. Acetyl-CoA is a two-carbon compound in the presence of a carboxylase, all right, a carboxyl group in the form of bicarbonate coming from biotin is added to acetyl-CoA. This is the carboxyl group of malonyl-CoA that came from your carbon dioxide carried by your biotin. Again, emphasizing to you that in carboxylation reactions, biotin is the source or carrier of your carbon dioxide. Okay, next reaction. Okay, this is your thiamine pyrophosphate. It is derived from your what? Thiamine or vitamin B1. All right, this is the structure of thiamine. Meron siyang pyrimidine ring, meron siyang thiosulfate. Again, you don't have to memorize all of this, no? How do you convert your thiamine into TPP or thiamine pyrophosphate? In the presence of TPP synthase plus ATP here, okay, your thiamine becomes thiamine pyrophosphate. All right? Ito yung thiamine pyrophosphate there. Okay. Now, what is important about your thiamine pyrophosphate? It contains a carbon atom here, a reactive carbon atom 2, which is the carrier of aldehyde groups. It is the carrier of aldehyde groups in reactions that need the transfer of aldehyde groups from one compound to another compound. That would be your thiamine pyrophosphate coming from your thiamine or vitamin B1. All right, this is an example of a reaction that utilizes your thiamine pyrophosphate. Okay, this is this is a summary of your hexose monophosphate shunt or pentose phosphate pathway. This is one of the major carbohydrate metabolic pathways. In this pathway, glucose 6 phosphate coming from glycolysis is shunted toward the oxidative phase to synthesize your NADPH here, and your ribose 5 phosphate in the non-oxidative phase. Ribose 5 phosphate is used in the synthesis of your what? Nucleic acids and nucleotides. No? In this reaction, your ribose 5 phosphate undergoes transketolation reactions catalyzed by your thiamine 5, I'm sorry, catalyzed by transketolase in the presence of thiamine pyrophosphate. as a cofactor here. Okay. Again, here, in another transketolase reaction here, thiamine pyrophosphate is again a cofactor here. So thiamine pyrophosphate is a cofactor of certain enzymes involved in a number of metabolic pathways. This time, we're talking about your pentose phosphate pathway or your hexose monophosphate chain. All right. This is pyruvate dehydrogenase. This is isocitrate dehydrogenase. This is alpha ketoglutarate dehydrogenase. Your pyruvate dehydrogenase converts your pyruvate coming from glycolysis into acetyl-CoA that occurs in the mitochondria, catalyzed by this enzyme in the presence of your thiamine pyrophosphate as a coenzyme or cofactor here. Okay. Now, your isocitrate dehydrogenase here in this reaction convert your isocitrate into alpha ketoglutarate with thiamine pyrophosphate as a coenzyme. Again, in your alpha ketoglutarate reaction, your alpha ketoglutarate is converted to succinyl-CoA in the presence of thiamine pyrophosphate. So it tells you, therefore, that most of your coenzymes help extract energy from the body, from the food that we eat. Okay? It is not a source of energy per se, okay, but they help extract energy from the food that we eat. And for that is food, your carbohydrates, fats, and proteins. All right? So if you are not eating, if you do not eat, there is no source of energy, okay, from which your vitamins can extract, isn't it? Can extract. So you have to eat to have energy. There is a misconception that if you take in vitamins, that is good for you. You become strong, you become energetic, etc. That's not correct. Hmm? Sige. Ano oras ka uwi? Okay, sige. All right, any question about vitamins so far? Let me repeat, no? Vitamins do not give us energy. It is the food that we eat that we get vitamin with energy. Your vitamins only help to extract energy from the food. So the moral of the story is, dapat kumain tayo. Hmm? Dapat kumain tayo. And of course, most of our food contain vitamin that help us in extracting energy, okay, from the food that we eat. So this is thiamine pyrophosphate. All right. Okay. In the catabolism of your branched chain amino acids, your valine, isoleucine, and leucine, of course, you'll take this up in the amino acid metabolism problem in the second semester. Somewhere here, you convert your valine, isoleucine into leucine into certain intermediates here, catalyzed by this enzyme. And this enzyme utilizes your thiamine pyrophosphate as a coenzyme or a cofactor. All right, next. Okay, we're done with NAD+, we're done with biotin, we're done with um, thiamine. This time we're talking about your riboflavin, which is whose coenzyme form is flavin adenine dinucleotide. All right? Ito yung structure ng riboflavin. Again, you don't have to memorize the structure. All right? To convert this into FAD, this is initially phosphorylated by a kinase enzyme, your flavokinase, in the presence of ATP. So from riboflavin, it becomes flavin mononucleotide or FNN. meron siyang isang phosphate group. Saan ang isang phosphate group natin? There, coming from ATP. All right. This is further phosphorylated by another ATP molecule. So that from riboflavin, it becomes FMN. It becomes now flavin adenine dinucleotide here. Now, what is important in this FAD? You have two. Okay, you have two hydrogen atoms here in the isoalloxane ring. All right, that are what carriers of hydrogen atoms containing one electron. Ito mga importanteng functional group in your FAD. So these are acceptors of hydrogen atoms from certain substrates. Okay? From certain substrates. Let me proceed further. Okay, so this is your citric acid cycle or your Krebs cycle. Okay, so at this point, you don't have to memorize your Krebs cycle. I'm just showing you reactions wherein FAD is a coenzyme of a particular enzyme. All right. In the conversion of succinate to fumarate here, catalyzed by succinate dehydrogenase, FAD accepts a hydrogen atom from succinyl CoA, and therefore FAD becomes reduced to FADH2. Succinyl is now oxidized into fumarate. Again, let me repeat. Reduction means addition of hydrogen atoms. Oxidation would be or removal of hydrogen atoms. So your citric acid cycle there utilizes in one of the steps your FAD as a cofactor. In the process, it is reduced to FADH2. Okay? Did you get that? Okay. All right. This is, okay, let me just try to expound this further. The same, no? Take a look at your succinate. No? It has 4 carbon atoms. There is a carbon to carbon bond here. In the presence of a dehydrogenase enzyme, pag sinabing dehydrogenase, tatanggalan mo ng hydrogen atom. All right? FAD here accepts 2 hydrogen atoms, one each from carbon 2 and carbon 3 of your succinyl CoA. In the process, your FAD becomes reduced to FAD2H, while your succinate here is oxidized into fumarate. Let me repeat. FAD is reduced to FADH2. This is the reduction part. Your succinate is oxidized into fumarate. This is your oxidation part, catalyzed by your succinate dehydrogenase. So a dehydrogenase, therefore enzyme, catalyzes an oxidation reduction reaction. Clear? Clear? Take note that in the conversion of succinate to fumarate, a double band is created between carbons 2 and 3 of your fumarate, while you have a single band between carbons 1 and 2 of your 2 and 3 of your succinate. All right. There is another reaction utilizing your FAD and FMN as a coenzyme of your nitric oxide synthase. All right. Your arginine here is converted into citrulline plus NO, nitric oxide here. And nitric oxide is a potent coronary vasodilator, which is useful in patients with angina pectoris. All right. So this enzyme here utilizes your FAD, FNN, your heme, as well as your tetrahydrobiopterin as other cofactors of your nitric oxide synthase. Again, you don't have to memorize this. I'm just showing examples where you know FAD and FNN are coenzymes or cofactors of certain enzymes. Any questions so far? Any questions so far? Oh, wala daw. Okay. These are the reactions in your beta oxidation of fatty acid. Pag sinabing beta oxidation, your fatty acid is converted into acetyl-CoA. Acetyl-CoA is converted into energy, and therefore beta oxidation occurs when there is limited supply of energy, as in late starvation or fasting. Okay, you have not been eating for, let's say, more than 24 hours, 3 to 4 days or even longer, and therefore your fatty acids are being converted into energy in the form of acetyl-CoA. And the reactions involve several steps: activation, oxidation, hydration, oxidation, thiolysis. In this oxidation step, here, your palmitic acid, an example of a fatty acid being converted into its active form, palmitoyl-CoA here, is oxidized into delta 2 transenol CoA with FAD as an acceptor of two hydrogen atoms from palmitoyl CoA. In the process, your FAD is reduced to FAD2H. Your palmitoyl CoA is oxidized into delta 2 transenol CoA. Again, you don't have to memorize this. No? I'm just showing you reactions wherein FAD is a coenzyme of a particular enzyme. This is your acyl-CoA dehydrogenase. Dehydrogenase, again, is an enzyme that catalyzes an oxidation reduction reaction. Okay, clear? Any questions so far? Walang mag-question, ha? All right. This is your pyridoxal phosphate. This is the structure of pyridoxal phosphate, a vitamin 6 derived coenzyme. Pag sinabing pyridoxal, galing sa pyridoxine, your vitamin B6, involved in carbohydrate, amino acid, and transmitter synthesis. No? All right. The important thing about your pyridoxal phosphate, you have an reactive functional aldehyde group here that is involved in the transfer of amino groups, especially in transamination reactions. Pag sinabing transamination, you transfer amino acid from one amino acid to the other amino acid. And therefore, pyridoxal phosphate is famous for its being a what? Cofactor in transamination reactions in amino acid metabolism. Hmm? In amino acid metabolism. It is for this reason that your pyridoxal phosphate is called your amino acid vitamin, primarily because it is involved in transamination reactions or reactions involving the transfer of amino groups from one amino acid to another amino acid. All right, that will be your PLP, pyridoxal phosphate. All right, I'll give an example wherein your PLP is a cofactor, no? This is your glycogen. Glycogen is the storage form of what? Carbohydrates in animals or men. Starch is the storage form of carbohydrates in plant, no? In times of early fasting, hmm? Early fasting, 8 to 12 hours hindi ako kumakain. All right, your glycogen reserves are broken down into glucose units, catalyzed by your glycogen phosphorylase enzyme in the presence of PLP as a coenzyme of your glycogen phosphorylase. And therefore, your glycogen is broken down into glucose units. All right, needed by the body in times of early fasting or early starvation. That would be your PLP, peridoxal phosphate. All right. Here, this is also involved in heme synthesis. No? Heme synthesis, you synthesize heme. Heme is present in your red blood cell. Red blood cell contains your red pigment, heme plus globin. It is the heme part that imparts the red color of your red blood cell. In the synthesis of heme, you have two substrates, succinyl-CoA plus glycine, an amino acid here, catalyzed by this enzyme in the presence of peridoxal phosphate. It's a coenzyme. Until finally you synthesize your heme. Okay. It would be easy, therefore, to imagine that with pyridoxine deficiency, all right, pyridoxine deficiency, what would be the effect on heme synthesis? Decrease, correct? And therefore, patients with pyridoxine deficiency would what? Develop anemia. They develop what we call anemia. So one of the clinical manifestations of patients with pyridoxine deficiency would be anemia. All right, that would be your PLP. Another reaction wherein PLP is a cofactor. This is histidine, an amino acid. No, it is decarboxylated into histamine by a decarboxylase enzyme, histidine decarboxylase. All right, this is removed by decarboxylase, and this is released as carbon dioxide. Histidine is converted into histamine. Histamine is a neurotransmitter that mediates a wide variety of allergic and inflammatory responses. No, if you develop allergy, kumain ka ng maraming itlog or chicken or chocolates or shrimp, all of a sudden you develop itchiness because of high levels of histamine in your body. In other words, there is decarboxylation of histidine into histamine. And treatment would be to give antihistaminic. Again, PLP is a cofactor of a decarboxylase enzyme here. Alright? Okay. Ito yung sinasabi ko. PLP is a cofactor in your transamination reactions. Trans means transfer of amino acids, amino group here. Alright? This is an amino acid, alanine. Meron siyang amino group. Alright? Meron siyang amino group. In the presence of alanine aminotransferase, in the presence of alanine aminotransferase, this amino group here, alright, is transferred to PLP. And PLP, it is a transient carrier of the amino group coming from amino acid. Ililipat kayo yun sa alpha-ketoglutarate. All right. And what happens alpha ketoglutarate? The alpha ketoglutarate becomes glutamic acid, another amino acid, where your alanine becomes a keto acid. So this is the essence of transamination in the presence of PLP as a transient carrier of the amino groups. Okay. You'll meet this more extensively when we discuss amino acid metabolism in the second semester. All right. Again, in the synthesis of your serotonin and melatonin, these are neurotransmitters, the starting substrate is tryptophan. And somewhere along the way here, you have tryptophan decarboxylase catalyzed by this enzyme in the presence of PLP. Serotonin and melatonin are neurotransmitters involved in a number of metabolic reactions. Okay, next question. John, which coenzyme is mainly involved in transamination of amino acids? Ison, Pauline?
Good morning, Doc. Letter D po, PLP.
Your PLP, that's correct. Hmm? Good. I'm sorry, this should be NADP, hindi NADPF. So the answer here would be peridoxal phosphate there. All right. Now, the second classification of your enzyme would be your metal ions, no? These are your inorganic metal ions or ion sulfur centers, no? All right. So zinc is a cofactor of your carbonic anhydrase, etc., etc. Down the line here. Chloride is a cofactor of soluble amide. In other words, certain enzymes, no, function in the presence of metal cofactors. All right, metal cofactors. I'll give an example here. Okay, magnesium ion here is a cofactor of your hexokinase glucokinase. No? Hexokinase glucokinase phosphorylates your glucose into glucose 6 phosphate here. All right, in the presence of magnesium ion as a cofactor plus ATP. So this enzyme, if you're talking about kinase, kinase is a transferase enzyme. It is specific for transferring phosphate group from ATP. All right. This transferase enzyme transfers one of the phosphate group of ATP to carbon 6 of glucose. And in the process, your glucose becomes glucose 6 phosphate here. All right. That would be magnesium as a cofactor of your hexokinases or glucokinase. These are transferase now. This is the first step in glycolysis, by the way. This is an irreversible reaction. All right. Why is this an irreversible reaction, by the way? Why is this an irreversible reaction? Anybody?
It is an exergonic reaction.
That's correct. It is an exergonic. Take a look at this. The standard chain is negatively charged here, and therefore this is highly exergonic. This is highly irreversible. Hmm? All right. Your pyruvate kinase also utilizes your potassium as a cofactor. Pyruvate kinase catalyzes the what? Anong kamo? Hmm? It converts your phosphoenol pyruvate into pyruvate. Okay, that would be potassium as a cofactor of your pyruvate kinase. So this is this is the last step of your glycolysis, and this is the third of the three irreversible steps of glycolysis here. Next step. Okay, take a look. Zinc is a metal cofactor of carbonic anhydrase. Wala nang iba. In fact, zinc, okay, carbonic anhydrase is the only enzyme utilizing your zinc as a cofactor. All right. Next question. Hmm. Biglang awa. Nag-recite na ba si Baay, Tia? Tapos na, nag-recite, ano?
Hindi pa po, Doc.
Ay, hindi pa. Oh, Miss Baay, Tia Marie. Would you like to answer this? Choose the correct coenzyme chemical group transferred. Letter A, letter B, letter C, letter D.
Is it letter D po ba, Doc?
Huh?
Letter D.
Letter D. Letter D? Okay. Trisha, biglang awa. Do you agree with the Tia Marie?
Um,
No po, Doc. Letter A po.
Okay, letter A. Di ba sabi ko, pag carboxylation, biocytin or biotin, kaya tama ito. Coenzyme A acyl groups. Hmm? Okay, so it should be letter B. There. Okay, next. Burgos. Choose the correct enzyme metal cofactor pair. Letter A, letter B, letter C, letter D. Burgos, are you here?
Yes po. Hindi po ba?
Hmm?
Ay, A po pala.
So it will be letter A. Okay. Your carbonic anhydrase utilizes your zinc as a metal cofactor. All right. Metalloenzymes, enzymes that require a metal in their composition. All right, like your zinc, your what do you call this? Your carbonic anhydrase, it utilizes your zinc as a metal cofactor, and therefore it is a metalloenzyme. Hmm? Substrate is the molecule acted upon or targeted by the enzyme to form a product. That's easy to understand, no? All right. Here in this reaction, again, glucose is phosphorylated into glucose 6 phosphate, catalyzed by a transferase enzyme. Isn't it? Transferase enzyme. So glucose is the substrate. It is being converted into a product. But ATP is also a co-substrate here. Hmm? ATP is also a co-substrate primarily because one of the phosphate groups of ATP is transferred to carbon number 6 of glucose. And glucose 6 phosphate is phosphorylated into, I'm sorry, glucose is phosphorylated into glucose 6 phosphate. All right. This is an irreversible reaction, one of the three irreversible steps of glycolysis, primarily because the standard change is negatively charged here, correct? My question is, your phosphate or ATP has three phosphate groups. Your alpha, okay, your beta as your gamma. Hmm? Alpha, beta, and gamma. So kaya nga adenosine triphosphate. Now, in kinases reactions or transferases reactions, which phosphate group of ATP, okay, is transferred to glucose, carbon 6 of glucose? Is it the alpha, the beta, or gamma? Anybody?
Doc, yung alpha po.
Alpha. Bakit alpha?
Kasi esterified po yung band niya.
No. Alpha is not a ester band. No? It doesn't possess a high energy phosphate bond. And therefore, you're left with your gamma and the beta phosphate bond. Between the two, okay, which is usually transferred in phosphorylated reactions, it will be your gamma phosphate bond. So remember, it is the gamma phosphate bond, not the alpha nor the beta, but it is always the gamma phosphate bond. Okay? Alam niyo na ito, di ba? What is the difference between an enzyme and a hormone? You cannot hear an enzyme. Did you get the joke here? Hindi kayo tumatawa, ibig sabihin hindi nyo nakuha ang joke. Ha? You cannot hear an enzyme, but you can hear a hormone. Kayo naman, oh. Tumatawa si Franz, oh. Okay. Active site of the enzyme. Take note that the active site of the enzyme is just a small cleft, isn't it? Or a pocket. If this is your whole enzyme, this is just a small cleft or a pocket that constitute the active site of the enzyme to which your substrate is bound to. All right. And this active site of the enzyme consists of functional groups like certain amino acids, and most of these are polar amino acids: cysteine, serine, lysine, histidine, aspartate, from 2 to 4 amino acids. In other words, these amino acids line up this cleft or pocket, all right, to which a substrate can bind to. Plus, bound cofactors like your coenzymes, mostly your B vitamins, your prosthetic groups, as well as your metal ions. All right. So the active site of the enzyme contains multiple amino acids that line up the catalytic or the active site plus your bound cofactors. The rest of the enzyme would be your amino acids, no, that maintain the three-dimensional nature of your enzyme. Correct? Proteins have three-dimensional structure, and since enzymes are made up of amino acids, then enzymes also have a three-dimensional structure. So that would be your active site or catalytic site of the enzyme. Okay, gets nyo? Okay. What about allosteric site of the enzyme? Allosteric site is a site of the enzyme physically different from the active or the substrate or catalytic site. If this is an enzyme here, this is the substrate or the active, or this is another site here, different from the catalytic site, all right, to which certain allosteric molecules bind to. It is not the substrate that binds to the allosteric to the but it is an allosteric molecule that binds to. Now, your allosteric molecules are small molecules, no? They could be what? Positive or negative allosteric molecules. Pag sinabing positive, all right, once they bind to the allosteric site, they change the conformation of the catalytic site such that the activity of the catalytic site will be increased. And therefore, the allosteric molecule activates the catalytic site, and therefore it will hasten the catalytic activity of your enzyme. If it is a negative allosteric molecule, what would the effect? It will also change the conformation of the catalytic site, but the activity will be decreased. And therefore, a negative allosteric molecule will decrease the catalytic activity of a certain enzyme. So you know now the difference between the active or the catalytic site and the allosteric site. Clear? Any question about that? Okay, let me proceed further. Okay, let me ask Kalayag Nathan. Will you answer this? The catalytic activity. Ikaw na magbasa kaya, Nathan. Pagod na ako eh. Nathan. Ha?
Lagot ka, Nathan. Mali yung sagot mo. Mali si Doc.
Naglag ba ako? Can you still hear me? Okay. Kalyaw, anong answer dito?
Doc, yung A po, active site.
Okay, active site. Sige. Okay, this is regulatory or the key enzyme.
Doc, hindi po ata kayo nakapresent.
Ha?
Hindi po ata nakapresent yung PPT niyo po.
Hindi naka-present? Ano nangyari? You don't, hindi makita yung slide ko? Hindi makikita?
Hindi po, Doc.
Oh, ano nangyari?
Nawala po kayo kanina, Doc eh. Naghang po kayo.
Oh, sandali ha. Okay. Mag-leave meeting muna ako ha. Tapos papasok ulit ako ha. Okay, mukhang naghang ako. Okay. So regulatory or key enzyme there, enzyme that catalyzes the rate limiting or committed step of a metabolic pathway. A metabolic pathway consists of a series of reactions, no? Like glycolysis, no? It consists of several reactions wherein the product of the first reaction becomes a reactant of the second reaction and so forth, no? Until you form a final product. So that would be a rate limiting or committed step, no? In other words, the overall rate of the metabolic pathway depends on a particular enzyme that catalyzes the rate limiting or commodity step of a metabolic pathway. Here, I'll do an example here. No, here in glycolysis, glycolysis is a pathway wherein your glucose coming from the diet, carbohydrates, is converted into ATP and pyruvate or lactate. In the absence of oxygen, pyruvate is converted to lactate. It consists of 10 reactions, 3 of which are irreversible. The rest are reversible reactions, catalyzed, of course, by 10 enzymes. Okay. Now, phosphofructokinase, okay, catalyzes the phosphorylation of fructose 6-phosphate into fructose 1,6-bisphosphate. Fructose 6-phosphate has only one phosphate group, whereas your fructose 1,6-bisphosphate has two phosphate groups, one at carbon 1 and one at carbon number 6. Kaya nga fructose 1,6-bisphosphate. Your phosphofructokinase or PFK1 is the rate limiting or committed enzyme. Committed because it commits your glucose into further oxidation. No, it is a rate limiting or a regulatory enzyme because the criteria for rate limiting or committed enzyme is it catalyzes the slowest reaction in a given metabolic pathway. Yung pinakamabagal na reaction na ikakatalyze niya. That would be the qualification of a rate-limiting enzyme. Question, bakit dapat mabagal yung enzyme? Bakit hindi yung una? Bakit hindi yung gitna o bakit hindi yung last? Bakit yung pinakamabagal? Anybody can answer that? Let me see. Francis Castro.
Yes po. Ulit po.
Okay, ulit. Sabi ko, bakit yung rate-limiting enzyme should catalyze the slowest reaction in a given metabolic pathway?
Um,
Bakit hindi yung pinamabilis? O yung first reaction? O yung gitna o yung pinakahuli?
para tulungan po yung slowest.
Para tulungan nyo, eh bakit slow? Di ba dapat mas maganda pag pinakamabilis? Hmm?
Hindi ko po.
Sige. Hindi kayo nagbabasa, ano? Chavez, Mike Carey, Nicole.
Ano po, para po ba like makontrol po yung flow ng pathway po?
Eh bakit kailangan makontrol?
Siguro po yung mga resources like glucose, ganun po, mauubos.
Eh lahat naman ng enzyme nakokontrol ang flow ng ano eh, reaction, di ba? Like this one also, they also control the flow of reaction.
Siguro po sa
Anybody?
ATP na rin po siguro.
ATP na rin. Eh may ATP rin dito, eh, no? May ATP rin dito. Oh. Ito may ATP din, may ATP din dito. Anybody? Lisette Cruz? Okay.
Siguro po, Dok,
Sige.
kasi po, di ba, rate limiting. So, exactly meaning lang po niya is ililimit niya or i-control niya yung overall flux ng pathway.
Oo nga, iko-control niya. Bakit nga? Bakit nga doon sa specific enzyme na yon? When all of these enzymes also control the rate at which a reaction, ano? So, go back to my question. Why should a rate-limiting enzyme catalyzes the slowest reaction in a given metabolic pathway? Okay. Okay, there are certain allosteric molecules, no, that affect the activity of the enzyme. Allosteric, pag sinabing allosteric molecules, molecules that bind to the allosteric site of the enzyme. And these allosteric molecules, okay, will affect the activity of the catalytic or active site. For your allosteric molecules to produce the effect, dapat yung reaction mabagal. Otherwise, pag napakabilis yung enzyme activity, there will be no time for allosteric molecules to produce their effect on the active side of the enzyme. That is the reason why your rate limiting or committed enzyme should catalyze the slowest to give time for certain allosteric molecules to produce their effect. Gets nyo? Huh? Did I make myself clear? Ba't di kayo sumasagot? Are you still following me?
Yes po, Doc.
Okay, sige. All right. This is an enzyme that catalyzes a step in de novo synthesis of fatty acids. So acetyl-CoA is a regulatory enzyme. Acetyl-CoA here is carboxylated into malonyl-CoA. Again, with biotin, isn't it? As a carrier of your carbon dioxide in the form of bicarbonate, catalyzed by this. All right. There are certain molecules that allosterically activate your acetyl-CoA, like citrate, insulin, high carbohydrate, low fat, low protein, and certain negative allosteric molecules that inhibit the activity of your acetyl-CoA carboxylase, and therefore this will inhibit what or decrease the rate of de novo synthesis of fatty acid, while this one will increase the rate of de novo synthesis of fatty acids. So talk about what? Talk about a regulatory or a rate limiting enzyme, like your acetyl-CoA carboxylase. Next, in the synthesis of your cholesterol, one of the steps would be the conversion of HMG-CoA to mevalonate. Of course, this is followed by still another a lot of steps until you produce your cholesterol. This one is the rate limiting enzyme of your cholesterol synthesis, HMG-CoA reductase. All right, it catalyzes the slowest reaction to give time for certain allosteric molecules to produce their effect, like insulin, your thyroid hormone glucocorticoids allosterically activate your SMG-CoA reductase, and therefore they will increase the rate of cholesterol synthesis. On the other hand, your cholesterol, your bile acids, mevalonate, glucagon will allosterically inhibit your SMG-CoA reductase, and therefore this will decrease the rate of cholesterol synthesis. Statins are drugs that lower cholesterol level. So they inhibit your HMG-CoA reductase. And therefore, HMG-CoA or the earlier precursors like acetyl-CoA cannot be converted into mevalonate. Mevalonate cannot be converted into cholesterol via a number of steps. Okay, that would be a concept of HMG-CoA reductase as a rate limiting or a regulatory enzyme. Next. This is your pentose phosphate pathway. Your glucose 6 phosphate here, dehydrogenase, is a rate limiting enzyme. It is a rate limiting enzyme of your HMA or pentose phosphate pathway. Again, it catalyzes the slowest reaction in a given metabolic pathway. Next. Okay. So, lovely Dilemos, so will you answer this question?
Good morning po. A
Morning.
question, which of the following is true of the characteristics rate limiting enzyme? A. Catalyzes the first irreversible step of metabolic process. B. Catalyzes the slowest reaction in a multi-step pathway. C. Found in the last few steps of a metabolic pathway. And D. Is activity is not affected by allosteric molecules. The answer po is B. Catalyzes the slowest reaction in a multi-step pathway.
Good. O, alam nyo na ha. Okay, sige. All right. There's such thing as intracellular location of some important biochemical pathways. It just only tells you that some enzymes, no, okay, some pathways with their enzymes are located in certain, regions of the cell, like enzymes involved in glycolysis, HMB pathway, fatty acid synthesis are found in the cytoplasm here. On the other hand, these pathways with the enzymes are found in the mitochondria. Sa mga lysosome, ejects. So you have such thing as compartmentalization. You could just imagine, let's say, all the metabolic reactions or pathways occurring in the cytoplasm. Pag ganon, this will result to net consumption of energy, and this is not good for the economy of the cell. So compartmentalization of certain metabolic pathways is good because it is translated in terms of energy conservation within the cell. This is the meaning of what do you call this? Intercell location of some important biochemical pathways. Okay. Next, isoenzymes are enzymes with different amino acid sequences but catalyze the same chemical reactions. They act on the same substrate and produce the same product, but exhibit differing degrees of efficiency. Different isoenzymes expressed in specific tissues of the body. You'll meet this, no, as we go along. What are isoenzymes? Isoenzyme will be the same as your isozymes. Some books will label this as isozymes. Other books will label this as isoenzymes. No? In other words, different form of an enzyme. Okay, I'll give an example of an isoenzyme here. Of lactate dehydrogenase. No? Lactate dehydrogenase catalyze the conversion of pyruvate to lactate. Ay, sorry. Hello?
Hello, good morning, Floro.
Yes.
Oo. Sorry. Pwede ko kayang i-lecture yung platelets and hemostasis together with the intro to Metab on October 17?
Kailan ka ba dapat mag-lecture?
Nung platelet and hemostasis, online ngayon, online.
Okay.
Oo.
Sige, no problem.
Pwede.
Just remind me, just remind me. Baka makalimutan ko.
Kailan ko i-remind ikaw?
I-con mo na ako, i-viber mo ako.
Binahibar na kita.
Kasi nag-lecture ako ngayon eh.
Sige, sorry. Okay, sige. Thank you.
Okay, sige.
Okay, thank you.
Okay.
Okay.
Sorry, saan na tayo? Okay. It is a tetramer consisting of two subunits, M found in skeletal muscles and H found in the heart, no? So meron kang 5 distinct combination. Meron kang M3H, M2H2, MH3. Okay? Meron kang M4, meron kang H4. Since you're talking about a heart attack, it would be better to measure your H4 isoenzyme kasi H is specific for the heart. That's the meaning of what? Isozymes of your lactate dehydrogenase. Clear? So if a patient comes with signs of MI, you order for markers for MI, you should order for H4 of your lactate dehydrogenase, not M3H nor M4. Did you get my point there? Okay. But nowadays, of course, one of the most sensitive and useful marker of MI would be measurement of troponin. Hindi na masyadong ginagamit ang lactate dehydrogenase, but they use your troponin. And troponin, meron kang troponin 1, meron kang troponin 2. These are isozymes of your troponin. But of course, Your troponin is found exclusively in your cardiac muscle. And therefore, this is a good marker for, let's say, the presence of myocardial injury. All right. Enzymes, therefore, can be markers for what diseases. Okay. Are you still with me? All right.
Yes, po.
So this is classification of enzymes. No, you have oxidoreductases, transferases, hydrolases, lyases, isomerases, ligases, and these are subclasses. Classification is based on the nature of the reactions that they catalyze. Let me repeat, classification is based on the nature of the reactions that they catalyze. Okay, these are oxidoreductases. Transfer of electrons and hydrogen atoms from donors or reductants, hence oxidized to acceptors or hence reduced. Okay, the classic example here, lactate here is catalyzed by lactate dehydrogenase. It is an oxidoreductase, no? You know, because your dehydrogenase catalyzes the transfer of hydrogen atoms from certain donors to acceptors there. In the process, your acceptor becomes reduced. This one becomes oxidized. So this is an oxidation reduction reaction catalyzed by an oxidoreductase like your lactate dehydrogenase. All right. So this is transferase, transfer functional groups other than hydrogen like carbon, nitrogen, or phosphate from donors to acceptors utilize two products to produce, utilize two substrates to produce product. Okay, this one. Okay, your alanine transferase here catalyze the transfer of the amino group here to PLP. And PLP will transfer now the amino group to alpha ketoglutarate. In the process, your alpha ketoglutarate becomes an amino acid like glutamate, while your amino acid alanine becomes pyruvate. It utilizes two substrates to produce two products. That would be your transferases. Okay, kinases transfer functional group phosphate from ATP to an acceptor. Okay, hexokinase or glucokinase here catalyzes the transfer of the terminal phosphate group of ATP to carbon 6 of glucose here. And the process of glucose 6 phosphate is phosphorylated into glucose. Your glucose is phosphorylated into glucose 6 phosphate. So transfer functional group phosphate from ATP to an acceptor. All right. A galactosyl transferase here transfer galactose here. This is unactivated galactose, UDP galactose to ceramide. And therefore, your sphingomyelin here, your sphingolipid, your ceramide is converted into your cerebroside. This is one of the reactions in sphingolipid synthesis. So galactosyl transferase is a transferase enzyme. All right. Hydrolases cleavage of chemical bonds, no? Ester, ether, peptide, or glycosidic bonds by addition of water producing two products. This is pyrophosphate here. In the presence of water, this is cleaved here by a pyrophosphatase. You produce two molecules of inorganic phosphate here. Addition of water producing two products. You have put here plus two products. That would be your what? Hydrolase. So phosphatase is a hydrolase enzyme. Next, thiolase also is a hydrolase enzyme. Catalyze the cleavage of chemical bonds by producing two products. No? All right. This is beta ketoacyl CoA. All right. So this part is cleaved here. This part is cleaved. And this part is released as acetyl CoA. Right? And the rest would be your what? The fatty acid CoA with two carbons shorter. Okay, so this is thiolase. Next. This is sorry, naulit natin. All right. Lyase, like a dopa decarboxylase. It cleaves carbon to carbon, carbon to oxygen, carbon to nitrogen, bonds by means other than hydrolysis or oxidation. Okay. Let me just, this is dopa, 3,4-dihydroxyphenylalanine. All right. In the presence of the carboxylase, this is cleaved. So you have a cleavage of carbon to carbon bond here. Releasing this as carbon dioxide, converting your dopa into dopamine. This is dopamine. All right. Okay, so next. Again, your decarboxylase, lyase is your histidine decarboxylase is a lyase, no? Because it cleaves carbon to carbon bond here, converting your histidine into histamine. All right, so that would be your lyase. All right, this is citrate synthase catalyzes a physiologically important reaction that favors a carbon-to-carbon bond here. Carbon-to-carbon bond. So what happens here is ito yung carbon-to-carbon bond here. Oxaloacetate condenses with acetyl-CoA, catalyzed by synthase, converting your acetyl-CoA into citrate. You now synthesize a carbon-to-carbon bond. All right, so synthase is a lyase. All right, another layers here. Ba't nawala ako? Nawala ako?
Yes po, Doc. Pati po yung screen niya, Doc.
Ano nangyari? Nagcha-charge ako ng coin. Sandali lang, ha?
Baka gusto na po mag-break, Doc. Char.
Yun na. Sige, break muna tayo, ha? Break muna, okay? Sige. Hydrated into malate. All right? This is one of the reactions of your Krebs cycle. So hydratase is a lyase enzyme. Next, I think we're done with this. Okay. Now your isomerases transfer functional groups or double bands within the same molecule. Hmm? Your alanine racemase here, in L-alanine, the amino group is on the left side of carbon number 2, while in D-alanine, it is on the right side. So alanine racemase is an isomerase. It transfers functional groups or double bands within the same molecule. Next, your isomerase or your triose phosphate isomerase here, it transfers the phosphate group at carbon number 3 of your glyceraldehyde 3-phosphate to carbon number 1, converting your GADP into DHCP. All right? That would be your triose phosphate isomerase. No? Okay, your phosphohexoisomerase transfer functional groups or double band within the same molecule. This is glucose 6-phosphate and aldose is converted into a ketose, fructose 6-phosphate by phosphohexoisomerase. In other words, this enzyme, all right, catalyzes the interconversion between aldose and ketose sugar. All right, aldose and ketose sugar. Next, your mutase is an enzyme that transfer a phosphate group within the same molecule. In 3-phosphoglycerate, the phosphate group is at carbon number 2. In 2-phosphoglycerate, it is transferred to carbon number 3. This is 2. So functional groups like phosphate within the same molecule. That would be your phosphoglycerate mutase. This is one of the reactions of your glycolysis. No? Epimerase, transfer of functional groups or double bonds within the same molecule. So here, your cellulose 5-phosphate has a hydroxyl group at carbon number 3 on the left side. Dito naman, ribulose 5-phosphate, the hydroxyl group at carbon number 3 is on the right side. And therefore, these two compounds are C3 epimer. We call these your C3 epimers. No? They vary only in the position of your hydroxyl group at carbon number 3. All the rest pareho. All the rest pareho. So that would be your epimerase. No? This is one of the reactions of your pentose phosphate pathway. Now, this is ligase. Ligase joining of substrate in the presence of ATP. You have biotin here plus pyruvate in the presence of ATP. pyruvate is converted into oxaloacetate. 3 carbon plus 1 carbon, you produce 4 carbons, no? So join together in the presence of ATP. So pyruvate carboxylase is a ligase. It is a ligase, no? All right. Your adenosine synthase is also a ligase, no? It joins your aspartic acid and your citrulline in the presence of ATP to produce arginosuccinate. This is one of the reactions of your urea cycle. Next. This is another ligase, no? But necessarily doesn't require ATP. Your glycine condensing with succinyl-CoA in the presence of your gamma aminolevulinic acid synthase, converting your succinyl-CoA into your gamma aminolevulinic acid, one of the reactions of your heme synthesis. Question. Sige, susunod. Sino magbabasa niyan? Let me see. Greg Rafael De Leon.
And the enzyme that cleaves peptide bonds belong to which of the following general classes of enzymes?
What's your answer?
Lyase po ba, Doc? Letter C.
Okay, that would be lyase. You know, cleave, ibig mo sabihin, pinapalayas mo. So lyase, layas. That's your clue there, isn't it? It will be lyase, correct. Ano ba ibang question? Let me see. Okay, choose the correct enzyme chemical reaction catalyze pair. Melanie, John Melanie De Leon, will you try to answer that?
Opo, Doc.
Okay, yeah.
Choose the correct enzyme chemical reaction catalyzed pair. Case.
Basahin mo.
Okay. Choose the correct enzyme chemical reaction catalyzed pair. So, ang sagot po is yung sagot po, Doc, yung letter D, oxidoreductase transfer of hydrogen to an acceptor.
Okay. Yun ang answer mo.
Opo.
Okay, tama. Okay. Next question. What kind of reaction? Sige, pakibasa. Regente Juneda.
What kind of reaction is present in the interconversion of aldose and ketones? Ano po, Doc? Isomerization po, letter B.
That's good. That's correct. Isomerization. Okay. Okay, characteristics of enzymes, they are not changed by the reaction they catalyze, no? Although they participate in the overall reaction process, they are regenerated at the end of the reaction for reutilization or reuse. Although some reactions, no, at toward the end of the reaction, the enzymes are modified, but there is a certain step wherein they are regenerated back. So in other words, there is no net consumption of enzymes, no? Because they can be utilized. No? They do not invent new reactions. They simply make reactions occur faster. All right? That would be, they are not changed by the reaction they catalyze. No? They do not change or alter the equilibrium position of a chemical reaction. They cannot alter the laws of thermodynamics, hence they do not change the equilibrium position of the reaction or the standard free energy change of the reaction. In other words, in the presence of an enzyme, the reaction runs in the same direction, either forward or backward, as it would without the enzyme, just more quickly or more rapidly. Okay, the amount of product formed is the same whether or not the enzyme is present, but the amount of product formed per unit time when the enzyme is present might take hours or centuries to form if the enzyme were absent. Hmm? If the enzyme were absent. For example, carbonic anhydrase catalyzes its reaction in either direction depending on the concentration of the reactant. When there is high concentration of carbon dioxide in the tissues, all right, as a product of metabolism, the forward reaction favors the formation of your carbonic acid. Carbonic acid. When there is low concentration of carbon dioxide in the lungs, your bicarbonate, carbonic acid is converted to carbon dioxide and water, catalyzed by your carbonic anhydrase. All right? Next, enzymes increase reaction rates by decreasing activation energy. It seems confusing here because you have increase and yet you have decreased activation energy, isn't it? Okay. So remember, they increase reaction rates by decreasing the activation energy. Anong ibig sabihin nito? Okay, this is the coordinate, this is the energy profile of a reaction. We call this your reaction coordinate diagram. On the x-axis, you plot your reaction progress in terms of hours, and on the y-axis, you plot the standard or the energy change or your delta G. Okay, for a certain substrate or reactant in it, it must be converted to a product. Clear? Okay. Now, substrates or reactants, for them to be converted to a product, must reach an intermediate transition state. Meron kang transition state before they can be converted into a product. Okay? Now, in the presence of, in the absence of enzymes or uncatalyzed reaction, here, there is a high energy of activation. In other words, you activate your substrate or enzyme, you need high energy of activation to reach a transition state of the substrate before they can be converted to a product. All right. However, in the presence of an enzyme, the activation energy needed to convert your substrate or reactant to a transition state is much, much lower. And therefore, since you have a lower energy to reach a transition state, the reaction or the formation of the products would be much faster than in the absence of an enzyme. Did you get that? Okay, let me repeat. For substrates or reactants to be converted into products, they must reach a transition state, okay, before they can be converted to product. In the absence of enzymes, okay, the amount of energy needed to activate your substrate towards a transition state is much higher. However, in the presence of enzyme, the energy activation is lower, and therefore, the faster will be the formation of the product. Clear? Okay, kaya nga sinabi dito, they increase by decreasing the activation energy. Okay, that would be your characteristic of an enzyme. Like, I'll give an example here. Catalase catalyzes the breakdown of your hydrogen peroxide into water and oxygen. Hydrogen peroxide is a what do you call this? A superoxide, and it is a reactive oxygen species. No? It is an oxidant, and it can cause damage to cell membranes, damage to tissues. There is an enzyme in the body that converts your toxic hydrogen peroxide into less toxic form, like water and oxygen. Okay. In the absence of catalyst like catalase, this is the activation energy that is needed in it to convert your hydrogen peroxide into water and oxygen. However, in the presence of an enzyme, you only need this much activation energy, isn't it? So that your hydrogen peroxide can be easily converted on faster into water and oxygen. That's the meaning of enzymes, okay, lower the activation energy. They increase reaction rate by lowering the activation energy. Here, you need at least 18 kilocalories per mole of energy, but in the presence of an enzyme, you only need this much, 5.5 kilocalories per mole of energy. Okay? They are highly specific for the reactants absorb the catalyzed the alcohol and catalyze on only one type of chemical reaction. So talagang specific sila. They're highly specific. Okay. I'll give an example here. All right. Your carbonic anhydrase does nothing except catalyzes the synthesis of your carbonic acid from carbon dioxide and water. So we call this absolute specificity. We call this absolute specificity. Next, again, your catalase does nothing except the reverse. I mean, the hydrolysis of or the breakdown of your hydrogen peroxide into water and oxygen. Again, that is absolute specificity. Next, your glucokinase here, glucokinase, absolute specificity. Glucokinase catalyzes only the transfer of what? ATP into glucose 6 phosphate, into carbon 6 o glucose. Hindi pwedeng carbon 5, hindi pwedeng carbon 4, hindi pwedeng carbon 3, carbon 2, carbon 1. That's how specific is your glucokinase, no? The other thing about glucokinase is it is only the gamma phosphate bond, phosphate group of ATP that is transferred to carbon 6 to glucose, not the beta nor the alpha phosphate group of ATP. That is the meaning of absolute specificity. All right. Susunod, what else? All right. This is a stereo. Stereo means space, no? Your lactate dehydrogenase catalyzes the oxidation of L-lactate into pyruvate. Not D-lactate, L-lactate lang. All right? This is the meaning of stereospecificity of enzyme. Next, this is group specificity. Anong ibig sabihin ng group specificity? Hexokinase also catalyzes the conversion of other hexoses like glucose, galactose, and mannose into their phosphorylated forms. Glucose 6 phosphate, galactose 6 phosphate, and mannose 6 phosphate. So that would be group specificity. All right, next, mostly these are proteins in nature, although a small number of RNA-based biological catalysts like ribozymes or catalytic RNAs have also catalytic activity. In other words, they catalyze RNA splicing. Okay. Who would like to answer this? Let me see. Angelica Rose Ispornia. Isporna, would you like to read the question? Isporna.
Yes po, Doc.
Yeah.
Enzymes accelerate chemical reactions by A. Forming an activated complex with the substrate, B. Increasing the equilibrium constant of the reaction, C. Inducing a conformational change in the substrate, lowering the energy of activation of the reactants. Wait lang po.
So what's your answer here?
Letter D po, Doc.
Letter what?
D po, lowering the energy of
Okay,
activation.
letter D or dog. That's correct. Lowering the energy of activation of your reactants, no? All right. Next, Estrobo, Froilan, Ernestine.
The following the following are characteristics or properties of enzymes except they changed in a reaction, B hasten rates of reaction, C have high specificity, D proteins in nature. Um, except change in a reaction.
Okay, that's correct. Di ba sabi ko, they are not changed in reaction. They are regenerated for reutilization or reuse, no? The reason why I'm asking these questions, no? Because it tells me na yung those that I lectured earlier, naintindihan ninyo. Isn't it? Gets nyo yun? Do you appreciate
Yes
this
po.
way? Nakakatulong ba sa inyo yun?
Opo.
Ha?
Yes po.
Talaga, ha? Baka naman nahiya lang kayo magsabing hindi. Hmm? Okay, next. So, sino ka? You are Istrobo, no? Don't worry, lahat kayo mag-recite, no? Okay. Next, Galamiton, Jane.
Which of the following statements is true of the nature of enzymes? A, all require cofactors for their activity. B, their activities are maintained when broken down into component amino acids. C, they are mostly made up of glycoproteins. And D, they exhibit a high degree of specificity for their substrate. Uh, D po, Doc.
Letter D. Okay. Let me see kung tama ba yun. All right, that's correct. So you are Galamiton, no? Meron pa ba? Okay. Next, Garcia Faye Charmaine.
Which of the following statements about enzymes is correct? A. They affect reaction rates in the forward and reverse directions. B. They are permanently altered following the conversion of a substrate to a product. C. They are small molecules that are heat stable. C. Di na po to na. They will determine whether a reaction will take place.
Oh.
A po, they affect reaction rates in the forward and reverse directions.
Okay, that's correct.
Yep.
Kanina sa exam, ba't ang bilis nyo natapos?
Masyado daw po madali, Doc.
Masyadong madali? Oh
Joke
my
lang.
God.
Joke lang daw. Nanghula. Char.
Nasyak ako eh. After 5 minutes, ang daming natapos eh. Siguro dapat susunod, hirapan natin ang exam, ano? Alright. Iyan, ano? The effect in the forward and reverse. Catalyze, enzyme catalyze. These are letter A, mali. There are large molecules that are unstable at certain extremes of temperature. Letter C, it is the actual change in free energy that determines whether a reaction will take place or not. Letter D, enzymes are not changed during a reaction. So that makes letter B the correct answer. Okay. Break muna tayo, enzyme kinetics, no? Ito medyo mas mahirap pa. Enzyme kinetics. How do enzymes work? Ang sabihin ng enzyme kinetics. Break tayo ng 5 minutes. Okay? Sige, okay. All right, can we resume? All right. So this will be our objectives for enzyme kinetics. Anyway, I have mentioned this earlier during the first part of the lecture. Okay. When we talk about enzyme kinetics, we talk about mechanism by which enzymes bind substrates and turn them into products. All right. This is enzyme substrate complex formation. This is the first step in enzymatic catalysis, no? Dali lang, eh. This particular graph illustrates the existence of an enzyme substrate complex formation. On the x-axis is plotted increasing substrate concentration, and on the y-axis is plotted the velocity. Okay. At a constant enzyme concentration, the reaction velocity increases with increasing substrate concentration until a maximal velocity is reached. Let me repeat that. No? At a constant or a given enzyme concentration, the reaction velocity here, the reaction velocity increases here with increasing substrate concentration until your maximal velocity or Vmax is reached. At maximal velocity here, the catalytic sites of the enzymes have been saturated or filled up with the substrate. Hence, further increases in substrate concentration will not increase the velocity. Hence, the fact that an enzyme catalyzed reaction has a maximal velocity suggests, although indirect, the formation of a discrete enzyme substrate complex. This enzyme substrate complex represents the formation of your transition state species, which then form the product. Now, mind you that the reaction velocity or the rate of a chemical reaction is difficult to determine, but can be measured in terms of the number of molecules of reactants that are converted into products in a specified period of time. All right. So since we're talking about enzyme substrate complex, this is an example of an enzyme substrate complex. So this is your substrate. This is your enzyme, which is cytochrome P450. So this is a ribbon diagram enzyme of a substrate enzyme substrate complex showing with the enzyme cytochrome P450 bound to your substrate camphor. Take note that the catalytic site of the enzyme is just a small pocket or a cleft. Pocket or a cleft. And the rest would be your amino acids comprising the bulk of the enzyme. This time it will be your cytochrome P450 with camphor as a substrate. So this is an enzyme substrate complex formation. All right. There are two models Nawawala ako. Nawala yung aking slide na naman. Habisin, nawala yung slide ko na naman eh. Ganito. Nawala uli ako. Habisin, nawala yung slide ko.
Yes po, Doc, nawala po.
Nangyari. Teka. Andali ha, magliboli ako ha. Okay, can you see my slide?
Yes po, Doc.
All right. So this is your Fisher's template key or lock and key model. Now, in this lock and key model, take a look at the configuration of the substrate. No? It is an exact fit of the active site of the enzyme, forming an enzyme substrate complex. Just like a jigsaw puzzle. Sanet, pag may jigsaw puzzle, dapat hanapin mo yung exact fit to form a picture. In other words, the active site of the enzyme complements the shape of the substrate. So we call this a lock, and similar to a lock and a key. You cannot open a lock unless you have a specific key for that. As simple as that. Isn't it? This is rather a rigid model. It doesn't take into consideration the three-dimensional character of your proteins or the three-dimensional character of your enzymes, because enzymes are made up of amino acids or proteins for that matter. And since because of this rigid rigid structure, a better way to explain your enzyme substrate complex formation would be your the next model, which is your Kostland's indot fit model. In other words, a key or a lock must do something else to accommodate a key. And this is, of course, your Kostland's indus fit model. All right, take a look at the configuration of the substrate and configuration of your active site. Magkaiba, di ba? Okay. In this particular model, as the substrate approaches the active site of the enzyme, there is a change in the conformation of the active site. nagbabago so that the substrate can be accommodated. Kaya nga induced fit model. The enzyme or the substrate induces a change in the configuration or conformation of the active site so that the substrate can be accommodated. It is an induced fit model. All right? In other words, doon sa kanina, yung unang model, like this model, what happens is the substrate and the enzyme always fit together. They always fit together. However, in your Costlands induced fit model, they only fit the substrate and the enzyme only fit upon binding. So this is the more acceptable model in terms of your enzyme substrate complex formation. In other words, the active site of the enzyme molds itself around the substrate to produce a perfect enzyme substrate fit. In other words, the functional groups in the active site of the enzymes are positioned in a way that promotes the reaction and improves the binding site of the substrate. No? This is the more attractive model. It replaces the earlier rigid lock and key model since the substrate binding site is viewed as a dynamic surface created by the flexible overall three-dimensional structure of the enzyme. All right. So much for your enzyme substrate. Okay, the basic mechanism of model of enzyme catalysis. This is your Michaelis-Menten theory, sometime in 1913. This is a simple model of enzymatic reaction. So for enzymes that catalyzes the conversion of a single substrate to a single product, the expression for the reaction includes three basic steps: letter A, letter B, and letter C. All right, the first step, free enzyme binds reversibly to the substrate here, all right, to form an enzyme substrate complex there, sometimes called the Michaelis complex. This corresponds to substrate binding. With the rate constant K1. K1 is the rate constant for the formation of your enzyme substrate complex. No? Now, there will be two fates of your enzyme substrate complex. First, it can dissociate to E and S. It can dissociate back to A with the rate constant K minus 1. All right, K minus 1 refers to the dissociation of your enzyme substrate to free enzyme and substrate. The second step, it can proceed to the second step. In other words, your ES can be converted to enzyme product. This is the catalytic step with the rate constant K2. So K2, the rate constant for the conversion of your ES to AP. This decomposition of ES to EP is the rate limiting or the irreversible step in the catalytic process. Okay. There will be two fate of your EP or enzyme product complex. It can be converted back to ES here with rate constant K minus 2. K minus 2 represents the regeneration of ES from AP, or it can proceed to the third step. And this is the third step. Enzyme is released from the P, all right, with the rate constant of K3. Okay. Take note that in all catalysis, the enzyme is regenerated at the end of the reaction. The end of the reaction. Now, this mechanism is restricted only to a single enzyme substrate reaction. In other words, the enzyme has only one substrate. So this is the basic mechanism model of enzymatic catalysis. It is applicable only to single substrate enzyme reaction. All right. Now, question. Let me see kung sino magre-recite. Kate Goodis, will you try to answer this? Please read the question.
This theory on enzyme action proposed by Koshland pictures the enzyme as changing in conformation with the approach of the substrate. A. Flexible site theory. C. Lock and key theory. B. Covalent catalysis. And D. Strain theory.
So what's your answer here?
Changing in conformation.
Mm.
A po.
Okay, your flexible site theory. That's correct. Okay. Next, Gera Iraminiel. Read the question.
Koshland's theory on enzyme substrate complex formation states that the substrate binds into a rigid pocket on the enzyme binding site.
Mm-hmm.
B fits into an exact shape on the enzyme binding site.
Mm-hmm.
C forms a different shape on the enzyme upon binding. D induces a suitable fit on the enzyme upon binding.
Okay. So what's your answer here?
A po.
Huh? Try to analyze
Letter D po.
letter D. Okay. Costland, diba? Induced fit model. You are Gera, no?
Yes po, Doc.
Gera. So the answer is letter D. Okay. Okay. Next, Hernandez Juliana Pay.
Which is true of the lock and key model of enzyme substrate binding?
Mm.
A. Enzyme and substrate have complementary geometric shape that fit into other.
Mm-hmm.
Po. A po.
Sino yung nagsasalitang yun?
Ay, sorry po, Doc. Meron din pong kasing nagsasalita sa bahay. A
Okay.
po yung answer.
A ang answer mo.
Apo.
Okay. Sigurado ka?
Yes po.
Tignan natin, ha. Sino yung nagsasalita sa bahay mo? Patayin mo muna, ha?
Sorry po.
Patahimikin mo muna, ibig sabihin. Okay. Okay, this is your Michaelis-Menten equation. If you try to express the model into an equation, this is your Michaelis-Menten equation. V is equal to the ratio of the Vmax times substrate concentration over the Km plus your substrate concentration, where V is the velocity at any time in terms of moles per time. Bmax is the maximal velocity or reaction rate. Km is the Michaelis constant for the particular enzyme under investigation. And, and S in bracket would be the substrate concentration in molars. Okay. Now, if you try to express this in terms of a saturation curve, we call this your Michaelis-Menten saturation curve in honor of Leonor Michaelis and Maud Menten in 1913. No? In other words, these were the scientists to draw this particular curve, and we call this your Michaelis-Menten saturation curve. This is a graphical representation of your Michaelis-Menten equation. Again, this is a model a curve that explains the kinetics of enzyme catalyzed reactions. No? And this is true only for non-allosteric enzymes. Ibig sabihin, mga enzymes without allosteric sites. Their activity are not affected by certain allosteric molecules. No? So on the x-axis is plotted increasing substrate concentration, and on the y-axis would be the reaction velocity. Now, key points in this curve would be marked by points A, B, and C. Points A, B, and C. For many enzymes, the rate of catalysis, VO, is defined as the number of moles of products formed per unit time that varies with your substrate concentration. Okay. For a given quantity or a fixed quantity of enzyme at relatively low substrate concentration, all right, the reaction velocity here linearly or correspondingly increases as substrate concentration increases and begins to level off and approaches a maximal velocity at higher substrate concentration. Okay. In other words, for a limited quantity of enzyme, the reaction velocity linearly increases as the substrate concentration increases until a maximal velocity is reached there at higher substrate concentration. This graph shows that maximum is approached asymptotically, meaning a hyperbolic curve or a rectangular hyperbolized form. Okay. Okay. I'm sorry. Okay. I told you earlier that points A, B, and C are our point of interest. Okay. At point A, mm, at point A here at point A, your substrate concentration is less than Km. Kung nandito ang Km mo, your substrate concentration is less than Km. Guess nyo, this is your point A. So substrate concentration is less than Km here. All right. And therefore, the reaction velocity is directly proportional to the substrate concentration, meaning only a small portion of the enzymes are filled up with the substrate. Pwedeng 1/3, 1/4, 1/8. Okay. At point B, however, at point B, 1/2 of the enzymes are filled up by the substrate, and therefore substrate is equal to Vmax. At point B, therefore, you have a half maximal velocity. Let me repeat. At point B, 1/2 of the enzymes are filled up by the substrate. And of course, the velocity is still dependent on the substrate concentration. So at point B, substrate concentration is equal to Vmax over 2, half maximal velocity. Clear? At point C, here, substrate concentration is greater than Km. Km here represents the substrate concentration at half maximal velocity. Again, let me repeat, at point C here, substrate concentration is greater than Km, and therefore you reach a maximal velocity. In other words, no matter how much you increase substrate concentration, the maximal velocity is no longer affected, primarily because all the enzymes have been saturated by your substrate. Clear? Therefore, at point A and B, because this is your first order kinetic. First order because there is still ongoing reaction between the enzyme and the substrate. At point Z, this is zero order kinetic primarily because there is no longer reaction between the enzyme and the substrate, primarily because all the enzymes have been saturated by the substrate. And no matter how much you increase substrate concentration, maximal velocity will remain. Hindi bababa. There is neither increase nor decrease of your maximal velocity. Therefore, first order means the rate of reaction is dependent or directly proportional to the substrate concentration. At zero order, meaning the rate of the reaction is no longer is independent of the substrate concentration. So Km, or the Michaelis constant Km, it is the substrate concentration required for an enzyme to reach half maximal velocity. Half maximal velocity. All right? It is half maximal velocity. So did you get this Michaelis-Menten saturation curve? You get here a hyperbolic curve or rectangular hyperbola. And this is applicable only to your non-allosteric enzyme. All right. This is a representation of a enzyme in the presence of a substrate here. Okay. Substrate is less than Km. Here, substrate is Vmax over 2. Here at point C here, substrate is less than Km. Well, S, ito yung mga substrate mo, and these are your enzyme. I get this from Harper. I think I got this from Harper. Okay? So, therefore, ano bang biological significance ng Km? It is the substrate concentration at which half of the active sites or the enzymes are filled up. It is an inverse measure of the affinity of the enzyme for the substrate. Okay, please try to remember this. The lower is the Km, the higher is the affinity of the enzyme for the substrate. The higher is the Km, the lower is the affinity of the enzyme for the substrate. Okay, let me repeat. The lower is the Km, the higher is the affinity, the higher is the Km, the lower is the affinity. All right. Ito. Okay. These are two enzymes with Michaelis-Menten saturation curve. Enzyme A, enzyme B. All right. Ito yung Km ng enzyme A. Ito yung Km ng enzyme B. Alin ang mas mataas ang Km? Enzyme A or enzyme B? Remember, Km is the substrate at half maximal velocity. All right. So, again, let me repeat. Mataas ang Km ng enzyme A kaysa enzyme B. Gets nyo? Are you still with me?
Yes po, Doc.
All right. Sige. Which enzyme has a low Km, high Km? Enzyme A, enzyme B.
Low Km po, Doc.
Yes. Enzyme A, enzyme B.
Enzyme B po.
Okay, that's correct. Which enzyme has a low affinity for the substrate? Enzyme A, enzyme B. Low affinity.
Enzyme A po.
Okay. High affinity?
Enzyme B po.
Okay. Kasi mas mababa yung Km niya. Alright, next. Which needs a lower substrate to attain a Vmax?
Enzyme B po.
Enzyme B. Okay? Enzyme A ang higher substrate, no? Kasi dito pa lang, kokonti yung substrate mo, may Bmax ka na agad. Ito, maraming substrate bago ka makaatin ng Bmax. That's the meaning of next. Okay, which enzyme exhibit first and zero order kinetics? A or B? Okay, try to analyze the two graph there. Which enzyme exhibit the first order and zero order kinetics? Sino dapat may mag-recite? Oh, James Lagman. Sige.
Enzyme B po.
Enzyme
B.
B. Yung enzyme A, walang zero order kinetics?
Yung, bali yung enzyme B po yung ano, sa first order, tapos yung enzyme A, zero order kinetic.
Di ba dapat silang dalawa? Regardless of whether one enzyme has a low K or high Km, both enzymes will exhibit first order and zero order kinetics. Ha? Okay. Sige. Palagay ko gutom na kayo. Ha? Di pa tayo tapos. Okay. So, let me see. James, you answer this.
Km or Michaelis constant is a measure of A, enzyme affinity, B, equilibrium constant, C, reaction rate, D, max velocity. D po.
Ha?
Yung D po.
B?
Di ba, D, yung max velocity.
Mali ah. It is a measure of what? Di ba kanina sinabi ko?
Enzyme affinity.
Enzyme affinity. The lower the Km, the higher the affinity and vice versa. It should be letter A. Sige.
A po pala.
Okay, next. Charles, I see. Charles Magat. Will you answer this, Charles Magat?
Which of the following statement is true when a substrate concentration equals Km in an enzyme catalase reaction? A few of the enzyme molecule are present as a ES complex. B, majority of enzyme molecule are present as ES complex. C, half of the enzyme molecule are present on as ES complex. D, all of the enzyme molecule are present uh, as ES complex. C po.
Okay, that's correct. Half. Kasi ano equals, substrate equals Km. So that would be letter B. Ay, tama. Letter C, I'm sorry. Okay. Okay, next. Okay, Marcelino, Grace, will you try to read that? Grace
Which is
Marcelino.
Okay po, Doc. Which is true of the attributes of Vmax? A, all enzymes are saturated by substrates. B, it is the point wherein S is equal to Km. C, it is the point wherein S is less than Km. And D, it represents upward slope of saturation curve. Doc, I think it's Vmax. A?
Oh, that's correct. A. All the enzymes are stuck with the substrate, no? Okay. Nagigets nyo yung enzymology? Okay. Okay, next. Romilly Matteo.
An enzyme with a lower Km indicates which of the following: A, high affinity for its substrate. B, less enzyme substrate complexes are formed. C, requires increased amount of substrate to be saturated. D, maximum velocity can be reached at high substrate concentration. A po, high affinity.
High affinity. Okay, good. Sige. Next, Medrano, Monique.
Which of the following relationship is correct? A, increased velocity. D, increased the velocity is increased affinity. B, increased velocity, decreased affinity. Or C, decreased velocity,
Bakit velocity?
decreased.
Why are you mentioning velocity? A, increase km, increase
Sorry
affinity.
po.
Hmm.
Increased,
Are you reading different PowerPoint?
hindi po. Sorry po, na-confuse lang po. Pero yung my answer po is letter D po. Decrease km po is increased in affinity.
Okay, sige. So, the lower the km, the higher the affinity. That's correct. Hmm? You're Matayo, no? Matayo ka ba, Medrano?
Medrano po.
Okay, Medrano. Okay, next. Okay, next, Mendoza, Khalid, Daphne.
The mechanism and constant Km represents which of the following? A. Dissociation constant of the ES complex. B. Substrate at Vmax divided by 2. C. Substrate at Vmax. D. Vmax at highest substrate. Letter B po yung answer ko.
Okay, letter B. It is substrate concentration at half maximal velocity. Okay. Ano ito? Let me just see. Okay. Um, this is a slide that shows you the Km and physiologic utilization of enzyme here. Take a look at this. No, glucose converted to glucose 6-phosphate, either by hexokinase or glucokinase. No, hexokinase is found in extrahepatic cells, in your red blood cells, while glucokinase is found in the liver and your pancreatic beta cells. Okay. Um, your Km for hexokinase is 0.1 ml. Your Km for glucokinase is 5 to 6 ml, millimoles per liter. Okay. So in terms of affinity for glucose, which has a high affinity for glucose, hexokinase or glucokinase, given these Km values? Sige, tanungin natin si Paraiso, Mark Justin. Let me repeat. Okay, go ahead.
Glucokinase po. Like, yung mas mataas po ang ano. Tama po ba?
Okay, let me repeat. Given these two values for Km, which enzyme has a higher affinity for glucose?
Higher affinity po. And si ano po? Hexokinase po.
That's correct. Kasi mas mababa ang Km niya.
Yes.
And therefore, given this, even in times of low blood glucose level, as in starvation, your hexokinase can phosphorylate your glucose into glucose 6-phosphate. And therefore, the brain is provided with enough energy even in times of low blood glucose level because hexokinase has low Km and therefore it has high K affinity for glucose. However, yung glucokinase, mataas ang kanyang Km, it has low affinity for glucose. Okay. The glucokinase therefore is active only when there is increased blood sugar level, as in after a carbohydrate-rich meal. Nagiging active lang siya. Samantalang hexokinase, very active kahit na mababa yung blood glucose level natin. Therefore, yield glucokinase, because it is active only in times of high blood glucose level, glucokinase what works towards is storing your excess blood glucose as glycogen. mm, as glycogen or storing glucose in terms of lipids, in terms of triacylglycerol. So did you not appreciate the difference between a high Km and a low Km for a certain enzyme? You know, if you give examples, it would be easy to understand, isn't it? Okay. So, so much for hexokinase and glucokinase. No? Meron palang question dito. I know you have answered that, no? Okay. Now, earlier, I presented to you your if you allow me to go back here, I presented to you your Michaelis-Menten saturation curve. Sana ba yun? If you allow me to go back, okay. So Michaelis, ayan. Here. Okay. Here, this Michaelis-Menten saturation curve, meron kang increasing sulfate concentration with increasing velocity until your Vmax is reached. So here, given this, you can easily compute for your Km as well as your Vmax kasi meron kang increasing substrate concentration. Right? So, halimbawa, meron kang 1 millimole, 2 millimole hanggang sa mataas hanggang ganon. And therefore, you can actually make a hyperbolic saturation curve. And based on this, you can compute for the Vmax as well as your Km here. I mean, Km as well as the Vmax. But this graph needs an infinite amount of increasing substrate concentration. Napakadami. Isn't it? Probably if you work in the laboratory and you try to make a saturation curve, you'll be working in the laboratory for several days or several weeks to be able to compute for the Vmax and Km. Kasi nga kailangan mo ng infinite amount of increasing substrate concentration. It would be cumbersome using your Michaelis-Menten to use this to be able to compute for the Vmax and Km of a certain enzyme. Now, some wise guy, okay, in the name of Lineweaver-Burke, okay, design a what? A curve that is a reciprocal of your Michaelis-Menten saturation curve. Pag sinabing reciprocal, alright, eto ngayon, ginawa nila your reciprocal, your Michaelis-Menten Burke reciprocal. On the s-axis, you get the reciprocal of your substrate, and on the v-axis, you get a reciprocal of velocity. All right? And then, you now have an increasing substrate concentration. All right? Tapos, gagawa ka ng line. All right? Gagawa ka ng line here that bisects your this is your y-axis, isn't it? They bisect your y-axis and extend that line into the negative x if this is your x-intercept, this is the negative area. Ay yung mga kumuha ng ano ba ito sa geometry or or ano? Is it geometry course or logarithmic course, no? If you extend the line, the linear line, in other words, the hyperbolic curve that you see in your Michaelis-Menten is now a straight line. That's why it linearizes your Michaelis-Menten curve. You now draw a straight line here and extend this line into the negative x-intercept. Okay. The point at which this linear line intercepts your y-axis is your what? Is your we call this your 1 over b intercept. And the point at which this linear line touches your negative x-intercept is equal to your x-axis or minus 1 over km. This is 1 over B max. All right. And this is slope is equal to km over B max. So if you know the value here and using this formula, you can compute for your B max. If you know the value here and use this formula, you can compute for your km here, even with limited amount of increasing substrate concentration. Yun ang advantage ng Lineweaver-Burke plot over your Michaelis method. You can compute for the Km and Vmax even with limited increasing substrate concentration. Gets nyo? Okay, so just remember this value, 1 over Vmax. This is minus 1 over Km. So if I give you a value here, okay, let's say you have this much amount of substrate only. You graph this, you extend your linear line to the negative x-intercept. And the value here, as your linear line bisects your y-axis is something like 30. Diba? 30, okay. Ito yung mga velocity. And then, the value here as your linear line intersects your negative x is something like minus 0.27. And knowing this formula, x-intercept is equal to minus 1 over km, y-intercept is equal to 1 over Vmax. You cannot compute for your km and Vmax by replacing that formula. So here, this is the formula. So if you try to rearrange the formula, Vmax is equal to 1 over y-intercept. Vmax is equal to 1 over 30, and therefore your Vmax is something like 0.033, okay, the millimoles per second here. And knowing this formula, you can compute for your Km. Just rearrange the formula. Km is equal to minus 1 over x-intercept. This is equal to minus 1 over minus 0.27. You have a Km of 370. So here, at Km of 3.70, the velocity is half maximal. But you're able to compute for your Vmax here, even with limited amount of increasing substrate concentration. All right? That would be your Lineweaver-Burke versus your Michaelis-Menten saturation curve. I guess this is part of your... I gave this way ahead of time para ma-compute nyo. I hope you computed for this. All right, and therefore you have these particular values and values there. Okay? Okay. So, will somebody answer this? Let me see. Paraiso. Nag-decide ka na ba, Paraiso? Tapos na, no? Are you finished? Mark, Justin?
Yes po, Doc. Tapos na po.
Okay. Liberty Pasawa. Will you answer this?
In comparison to the Michaelis-Menten curve, Lieberberg double reciprocal plot is a more accurate way of determining the max of a reaction because if A exhibits a rectangular hyperbole, A exhibits binding cooperative. C requires lesser amount of enzymes. D requires lower substrate concentration. Letter D po.
Letter D?
Po.
Okay, letter dog. It requires lower substrate concentration. That's correct. Okay, we'll go to the concept of reversible enzymatic inhibition. There are types. Meron kang reversible, meron kang irreversible. And then the reversal, you have competitive, non-competitive, etc. Okay. Ito, competitive inhibition there. All right. This is a substrate binding to its enzyme. Exact fit. Isn't it? kasi analog yung substrate with the active site of the enzyme. All right, here comes an inhibitor. Instead of the substrate binding to the active site, it is the inhibitor. Kasi ang inhibitor, substrate analog. Pareho sila ng shape ng substrate. Correct? In other words, the inhibitor competes with the substrate for the active site on the enzyme. We call this your competitive inhibition. Gets nyo? Okay. Your competitive inhibition can be overcome by increasing your substrate concentration. Tataasan mo yung substrate mo para ma-displace yung inhibitor. So we call this your competitive inhibitor. Okay. In non-competitive inhibition, all right, non-competitive, the inhibitor binds to a site different from the active site. Nagbabind siya. Pag-bind niya dito, yung catalytic site nagbabago. And therefore, your substrate cannot bind. Gets nyo? And therefore, the velocity will be decreased. Correct? You cannot overcome the inhibition by increasing your substrate because the substrate cannot displace your inhibitor. Correct? Versus dito, increasing substrate will displace the inhibitor. Kaya nga this is non-competitive inhibition. Gets nyo? Okay. Okay, I'll give an example of a competitive inhibition. Lovastatin is a drug that inhibits the synthesis of cholesterol. Ito yung rate-limiting enzyme, yung SMG-CoA reductase. Ito yung shape ng kanyang active site. Alright? The normal substrate would be your SMG-CoA. Ito. Dapat na-occupy niya doong active site. In the presence of lovastatin has similar structure as your SMG-CoA substrate. So this one will compete with this for the binding site on your reductase. Eventually, this one will be displaced. So lovastatin now will occupy this one, inhibiting now the synthesis of cholesterol. Therefore, statins inhibit cholesterol synthesis by competitive inhibition. If you would like to overcome this inhibition, you increase concentration of your substrate and therefore you displace your lovastatin. Okay, gets nyo yan? Sige. Alright. Again, this is one of the pathways of reactions in Krebs cycle. Malonate here inhibits your succinate dehydrogenase because malonate here has the same structure as your succinate here. So again, this is competitive inhibition by malonate on succinate dehydrogenase. All right, examples of competitive inhibition. Methotrexate is an anti-cancer drug. It is a chemotherapeutic agent. Ito yung structure ng methotrexate. Again, you don't have to memorize this, no? It inhibits your dihydrofolate reductase. In other words, it competes with your 7,8 dihydrofolate. Instead of this binding to this, it will be methotrexate. Correct? And therefore, you cannot convert your 7,8 dihydrofolate to tetrahydrofolate. Eventually, you cannot convert your DUMP into DTMP. And DTMP is used in the synthesis of DNA of cancer cells. And therefore, methotrexate is an anti-metabolite or anti-cancer. It inhibits the synthesis of DNA in cancer by inhibiting this particular enzyme. Okay? All right, next. Your thymidylate, I'm sorry, your 5-fluorouracil also is an anti-cancer drug. It is an anti-metabolite. In the body, it is converted by salvage enzyme into DFUMP, deoxyfluoridouridine monophosphate. And this one inhibits your thymidylate synthase. If this is inhibited, ito cannot condense with DUMP. Ito. This one cannot condense with DUMP. And therefore, you don't synthesize DTMP, which is needed in the synthesis of DNA by cancer cells. Again, your 5-fluorouracil is a competitive inhibitor of thymidylate synthase. So these are clinical applications, by the way. Okay. What else? No? You know what is decumarol? Ano ba decumarol? It is an anticoagulant, no? Ano nangyari doon? It is an anticoagulant? Sorry. Ba't nagkaganon? Okay. In the synthesis of your clotting factors, no, we call this your vitamin K dependent clotting factors. All right, your procymogens or inactivated clotting factors 3, 7, 9, and 10. These are your vitamin K dependent clotting factors, no? Okay, these are converted into mature clotting factors in the presence of vitamin K dependent carboxylase. Okay, in the presence of vitamin K, by the way. All right, until you regenerate your vitamin K here. Okay, your warfarin or decumarol somehow inhibits this particular pathway. You inhibit your vitamin K epoxide, and therefore you don't regenerate your vitamin K, which is needed in the synthesis of your clotting factors. So if this pathway is inhibited, wala kang vitamin K to synthesize your vitamin K dependent clotting factors. And therefore, the absence of vitamin K means there will be no blood coagulation, and therefore, the clinical manifestation of deficiency of vitamin K would be bleeding. Bleeding, okay. Kaya yung mga pasyenteng nag-anticoagulant, they are given warfarin, no? And warfarin is the active ingredient or the active, you know your rat poisons. Alam mo yung ano ba yung brand name ng rat poisons? What do you know about rat poison, the brand name? Ano ginagamit na pampatay ng daga? Racumen. Alam niyo Racumen? Ha?
Yes po, Doc.
Okay. Pag binigay sa daga, ano nangyari sa daga? Namamatay sila because of bleeding. Correct? After several days, may maamoy kang mabaho. Pala patay na yung daga. It doesn't cause instant death, no? It inhibits your vitamin K reductase, and therefore you don't synthesize your vitamin K, which is needed in the synthesis of vitamin K dependent clotting factors. Okay, that would be your warfarin, okay, or decumarol. Okay, meron tayong, I think we are done with this non-competitive inhibition. Okay, tapos na tayo dito. I think we're done with here. Okay. This is a summary. Just go over these types of enzyme inhibition. You have competitive, reversible, and you have your uncompetitive or irreversible inhibition. And this is the characteristic. And this will be the kinetic effect on the VM, on the Vmax, and the Km. Just go over this. These are self-explanatory to be able to understand the kinetic effect of, let's say, a competitive inhibition, non-competitive inhibition, as well as uncompetitive inhibition. Just go over this. Okay, question. Let me see. Sorry, we have to extend because I'd like to finish this. Liberty Pasawa. Oh, yeah, Pasawa. Will you try to answer that? Liberty.
Structural analog of the substrate that can bind to the enzyme active site is called A. Competitive inhibitor, B. Irreversible inhibitor, C. Non-competitive inhibitor, D. Uncompetitive inhibitor. Letter A po.
Ah,
Letter A po.
okay. It will be your competitive inhibitor, substrate analog. All right. Next, Pengson, Josel.
Question: which of the following is the behavior of an inhibitor in competitive inhibition? A binds with the substrate, B competes with the enzyme, C competes with the substrate, D irreversibly binds with the enzyme.
Ano
C
nga?
po.
Okay. Competes with the substrate. It competes with the substrate for the active site of the enzyme. Okay. Well, I'm happy na intindihan nyo kahit mahirap. Okay. Pineda, Angel Rose. Pineda. Yan na si Pineda. Iniwan tayo, kumakain na. Wala na rito? Hala, iniwan tayo. Pineda, are you here? Okay, Rabia, Patricia Marie.
Question: competitive inhibition can be relieved by increasing the concentration of the following: A. Enzyme, B. Enzyme substrate complex, C. Inhibitor, D. Substrate. B po ba?
Ha?
Enzyme substrate complex.
Mali. Palagay ko nagugutom ka na kaya hindi mo lang ma-answer. It will be substrate. Therefore, the substrate displaces the inhibitor. Diba? Okay. Okay. Next, Salvador, Andrea, Nicole. Salvador?
Doc,
Yes.
which of the following does not occur in uncompetitive inhibition? A decrease Km, B decrease Vmax, C inhibition is reversed by adding more substrate, D inhibitor combines with the CS. Letter C po.
Letter C, sigurado ka? Okay, that's correct. It is letter C. Salvador ka. You're Miss Salvador, ano?
Yes po, Doc.
All right. And these are the Lineweaver-Burke for competitive inhibition. You just go over this, no? These are self-explanatory. And this is for non-competitive inhibition, like your Lineweaver-Burke plot. And this is your uncompetitive inhibition. You go over this. And this is a summary of the kinetic effect of competitive, non-competitive, and uncompetitive inhibition. Okay? Okay, next. Santiago, Mariel.
Dok, may answer na pong nakalagay.
Ayaw nga, no? Anong nangyari? Oh, I'm sorry. Mali yung sequence ng results ko. Okay. Okay. Now, there's such thing as irreversible inhibition. An inhibitor permanently and irreversibly inactivates or incapacitates the enzyme, usually by forming a covalent band to the protein enzyme or as a transition state analog. Inhibitors are mostly toxic substances, either natural or synthetic. Your DIPF, aspirin, penicillin, allopurinol, and 5-fluorouracil are common drugs in this manner. No? Okay. You've heard of malathion poisoning? Malathion poisoning. Malathion is used by farmers to as an insecticide. No? Okay. Normally, your acetylcholine, this is the neurotransmitter in the neuromuscular junction, acetylcholine is degraded by acetylcholinesterase into choline here and acetate, right? Now, in the presence of your organophosphorus inhibitors, which is found in your malathion or insecticide, all right, your organophosphorus inhibitor forms a permanent. It condenses with your enzyme, enzyme, acetylcholinesterase, forming an inactive enzyme. All right, and therefore, being an inactive enzyme, your acetylcholine cannot be degraded by your acetylcholinesterase into choline and acetate. Therefore, there will be accumulation of acetylcholine in your neuromuscular junction. And the effect here would be predominance of your autonomic nervous system effect. Vomiting, headache, diarrhea, difficulty of breathing, etc. etc. The sarin gas attack that I earlier presented to you, conducted by terrorists in multiple subway trains in Tokyo, and sarin, I mean, and what do you call this? The use of your malathion as insecticide produces this particular effect. There is permanent inactivation of the enzyme, and therefore there will be persistent accumulation of your acetylcholine in your neuromuscular junction, and therefore there will be dominance of your autonomic effects. Okay? Your aspirin, alam niyo ang aspirin? Acetyl salicylic acid. There. It causes acetylation of your cyclooxygenase enzyme. Ito yung acetyl group ng aspirin. This is an enzyme, cyclooxygenase. An enzyme has a lot of protein amino acids. One of these amino acids will be serine. So in the presence of aspirin, there is acetylation of the serine residue of your active cyclooxygenase, converting your active cyclooxygenase into acetylated inactive form. And therefore, there will be no synthesis of prostaglandins that mediate pain, fever, and inflammation. Being so, your aspirin is used in the treatment of inflammatory conditions. Okay? Kasi ini-activate niya yon. Okay. Of course, your acetaminophen, you're familiar with this, are reversible inhibitors. No? So once your aspirin causes inactivation of your cyclooxygenase, we call this your suicide inhibition. No? Okay? Nagsuswidal yung nag-suicide, there is permanent inactivation of your enzyme. All right? Okay, ito naman sa penicillin, no? This is also a suicide inhibitor. Okay. You just try to analyze this and I mean my slide vis-a-vis my notes, which I should be given to you. Okay. Again, in the treatment of allopurinol or gout, in gout arthritis, you use your allopurinol. This is a drug that inhibits your xanthine oxidase enzyme, and therefore allopurinol inhibit the synthesis of your uric acid from your purines, Okay. Next, drugs that inhibit specific enzymes. So drugs working for humanity. We have a lot of these, no? Like your topoisomerase, the targeted by amrubicin, your treatment of alcoholism, antabuse inhibits your aldehyde dehydrogenase, captopril, treatment of hypertension inhibits your angiotensin converting enzyme. Down the line here, down the line here. Okay. This is Viagra or sildenafil. It inhibits your phosphodiesterase, and this is used in the treatment of erectile dysfunction among men. No? Let me try to review to you. Okay. This is angiotensinogen. It is converted, okay, into angiotensin 1 here by this, and then to angiotensin 2 by angiotensin converting enzyme. Angiotensin 2 causes what? Vasoconstriction as well as aldosterone-mediated renal sodium water absorption, and therefore increased blood or hypertension. In the presence of angiotensin converting enzyme inhibitors like your captopril, ramipril, perindopril, this is inhibited. And therefore, your angiotensin 1 cannot be converted into angiotensin 2. Therefore, there will be no increase in blood pressure. And these drugs decrease blood pressure via inhibiting this particular enzyme. So you should know your biochemistry before you can treat certain diseases. All right. Again, statins will inhibit your enzym reductase, and therefore there will be no synthesis of cholesterol. Okay. Next. Okay, this is Viagra. How does it corrects impotence? Impotence is inability to maintain sustained erection. All right. GTP is converted into GMP by your adenylate cyclase, and GMP is converted into inactive 5' GMP by your phosphodiesterase. Okay. Now, if your Viagra or sildenafil inhibits this one, inhibit niya ito, there will be no conversion of your GMP into inactive 5' GMP. Tataas ang level ng GMP mo. Cyclic guanosine monophosphate. And this one causes smooth relaxation and vasodilation in penile blood vessels. And therefore, Viagra is used in impotent. Again, impotent is inability to maintain sustained erection. Okay, so this is the action of your Viagra. It increases your cyclic GMP. All right, your cyclooxygenase here is inhibited by your aspirin, your selective COX inhibitors like your Celebrex here. If this is inhibited, there will be no synthesis of prostaglandins by your cyclooxygenase that mediate pain and fever inflammation. So all of these drugs will inhibit this one. We call this your COX inhibitors. Next. Okay, alcohol. Chronic alcoholism is treated by antabuse. This is alcohol. It is converted into acetaldehyde by alcohol dehydrogenase. Acetaldehyde is further converted into acetate and acetyl-CoA. These are the less toxic components of alcohol. This is the toxic component. This is the one responsible for the toxic manifestations of chronic alcoholism. All right. Now, antabuse is a drug that inhibits this enzyme. Okay. Are you still with me?
Yes po, Doc.
Okay. If this is inhibited, what will be the level of acetaldehyde? Bababa tataas?
Bababa po. Ay,
Tataas.
mataas.
Tataas. Eh, di ba sabi ko, acetaldehyde will be the one responsible for the unwanted manifestations of alcoholism. Tataas ito ang level mo. Ay, di ba mas pangit sa ano yon sa alcoholic? Eh, bakit ginagamit ito? Anong reason? Ha? Sige, isip-isip. Okay, let me repeat. If this enzyme if a drug like antabuse inhibits your acetaldehyde, this will increase and therefore the patient will experience more of the side effect of alcohol. Ano mangyari sa kanya ngayon?
Hindi na po siya iinom.
That's correct.
Kasi lasing na po siya. Char.
Hindi na iinom kasi mas marami siyang maramdaman. Oh, nakakatawa, no? Okay. But siyempre, nowadays, hindi na masyadong ginagamit ito because there are newer drugs, no? Like nicotine patch, etc. Okay. Just to tell you that there are certain enzymes that inhibit certain, substances, and therefore these are used to treat certain diseases. Okay, we have mentioned this, your methotrexate and fibrouracil. This is inhibited. This will inhibit this one, and therefore there will be a synthesis of DNA by your cancer cells. Okay. Now, in patients with gout arthritis, you give allopurinol. This will inhibit your xanthine here. And xanthine, if this is inhibited, there will be no synthesis of uric acid. And uric acid will be deposited in your joint responsible for your gouty arthritis. So allopurinol is used in treatment of patients with gout arthritis as well as in cancer therapy because if you're giving an antimetabolite, you are converting your purines into uric acid, into uric acid. Kaya bibigyan mo ng cyclopram doon para less synthesis of your uric acid. Okay? Okay, in terms of kinetics for allostatic enzyme, they do not follow the usual hyperbolic curve or Michaelis-Menten saturation curve for your simple non-allostatic enzyme. All right? Instead, they have a sigmoid curve, tawag namin dito, sigmoid curve. All right? Okay, that's the importance of your allostatic enzyme. They do not follow the usual Michaelis-Menten saturation kinetics, and therefore they don't have the hyperbolic curve but a sigmoid curve. This one looked like a letter S. That would be your okay. Next question, and would like to answer this. I think I have here. Sino pang hindi? Mariel Santiago.
The following are true of the characteristics of allosteric enzymes except A. Follow the Michaelis-Menten kinetics. B. More complex than other or non-allosteric enzymes. C. Possess sites that bind with effectors. D. Substrates bind to sites other than the active site. Ang answer ko po, Doc, ay A.
Okay. It does not follow the Michaelis-Menten saturation kinetics. All right. There are certain regulatory mechanisms affecting enzyme activity, feedback inhibition, allosteric, reversible, zymogen, induction or repression of enzyme synthesis. I can go through this rapidly. Pag sinabing feedback inhibition, a product inhibiting its own synthesis. Let's say this is an original precursor being converted into a product catalyzed by a number of enzymes. Once you get the product, this will now what? Inhibit the first enzyme, usually yung regulatory enzyme. That's the meaning of feedback. A product inhibiting its own synthesis. Correct? That is feedback inhibition. All right? Ito, feedback inhibition. Pyruvate is converted to acetyl-CoA by your pyruvate dehydrogenase complex. Eh kung marami ka ng level ng acetyl-CoA, this will inhibit your pyruvate dehydrogenase. So feedback inhibition. Ganito rin, no? Succinyl-CoA here, pag marami ka ng level, succinyl-CoA, you need not synthesize more succinyl-CoA, and therefore this inhibit this pathway. Or this succinyl-CoA can inhibit your citrate synthase so that you don't produce more of your succinyl-CoA. So simple feedback inhibition, a product inhibiting its own synthesis through negative feedback inhibition. All right, cholesterol synthesis. No? You start from acetyl-CoA hanggang makasynthesize ka ng cholesterol via your rate-limiting enzyme, SMD-CoA. Ngayon, pag mataas ng level ng cholesterol mo, this causes a negative feedback inhibition on your rate-limiting enzyme to decrease cholesterol. Correct? Okay. Now, your hexokinase enzyme of your glycolysis, glucose is converted to glucokinase by this enzyme. Pag marami ng glucose 6-phosphate, this is inhibited, isn't it? And therefore, there will be no further phosphorylation of glucose in the glucose 6-phosphate. Again, a product inhibiting its own synthesis. Okay? Okay. Ito naman sa allosteric, we have got this before. Allosteric modification. Meron kang allosteric modulator effector, either activator or inhibitor. It binds to regulatory allosteric site, conformational change in your in your rate limiting enzyme. The effect is transmitted to the active site, change in shape of the active site, and therefore you have altered activity of the enzyme. So this is allosteric modification. The role of the small allosteric molecules on the activity of the enzyme. Okay. Pakibasa na lang ito sa... Alright. Again, allosteric modification. Ito yung rate-limiting enzyme of your glycolysis. These are allosteric molecules that affect the activity of this. ATP citrate H ions are negative allosteric molecules that affect the activity, while AMP and fructose bisphosphate allosterically activate activity. And therefore, this one will increase the rate of glycolysis. This one will decrease the rate of glycolysis. ATP is a major product of glycolysis. Here, ATP. Sorry. Ito, ATP is a major product of glycolysis here. Kaya pag mataas ang level ng ATP mo na, you don't need to synthesize more ATP. and therefore ATP will allosterically inhibit this enzyme. Okay? Okay, when we talk about covalent modification, it means basically phosphorylation and dephosphorylation of the enzyme. Pag sinabing phosphorylation, you add a phosphate group to the enzyme. Pag sinabing dephosphorylation, you remove a phosphate group of the enzyme by the enzyme phosphoprotein phosphatase. So dito wala na siyang phosphate group, dito meron siyang phosphate group. Okay. Some enzymes are active when phosphorylated and inactive when dephosphorylated. So remember, in general, anabolic or biosynthetic enzymes are active when dephosphorylated and vice versa, while catabolic enzymes are active when phosphorylated and vice versa. Yan ang ibig sabihin ng covalent modification, either phosphorylation or dephosphorylation of the enzyme. Yung serine, yung threonine, yung histidine, residue of the enzyme can be either phosphorylated or dephosphorylated. No? Okay, ito yun. I'll give an example here. No? Your phosphorylase B degrades your what? Glycogen into glucose units. Glycogenolysis yon. Ang phosphorylase B is inactive, ang phosphorylase A is active. In other words, if it is phosphorylated, okay, it is active. If it is dephosphorylated, it is inactive. Okay? Dahil sabi ko, degradative enzymes are active when phosphorylated, inactive when dephosphorylated. Oh. So example of a catabolic enzyme which is active when phosphorylated, inactive when dephosphorylated. All right? Okay. Your pyruvate dehydrogenase also, this enzyme catalyzes the conversion of pyruvate to acetyl-CoA. Okay. It is a what? Catabolic or anabolic enzyme? Ano bang pyruvate dehydrogenase? Catabolic or anabolic? It is an anabolic enzyme, biosynthetic enzyme. All right? Okay, so undergoes also your covalent modification. These are a number of enzymes that are when dephosphorylated, these are active. When dephosphorylated, these are active, and inactive when phosphorylated. So just showing you that some enzymes are active and inactive when phosphorylated and vice versa. All right. Now, this is just to show you na covalent modification not only occurs when you have phosphorylation or dephosphorylation of the enzyme. Sometimes meron kang adenylation of the enzyme, uridylation of the enzyme, methylation of the enzyme. Again, you change the activity of that particular enzyme. Okay. So not only phosphorylation, but also adenylation, uridylation, methylation, as well as acetylation of the enzyme. All right. G proteins also cause conformational changes. Okay. You just go over this vis-a-vis my notes. Cymogen activation. Okay, blood coagulation involves the intrinsic and extrinsic pathway. So the liver synthesizes inactive clotting factors that are activated in a cascade manner. Example here, your factor 12 is converted into the active factor 12A, and factor 12A will now convert your inactive factor 11 into 11 active factor 11 down the line here until you produce an insoluble fibrin clot. Involve the intrinsic and extrinsic path. Intrinsic because the factors occur inside the cardiovascular system. Extrinsic because the factors occur outside the vascular system. Either way, the end product would be your insoluble fibrin. So sign activation meaning a precursor, an inactive clotting factor is activated into a active form. That's the meaning of cymogen activate. Cymogen means inactive. All right. Okay. Like some example, your prothrombin is activated into thrombin, active form by calcium. And thrombin now activates your fibrinogen into fibrin. And fibrin will now produce your insoluble hemostatic clot or the fibrin clot. All right. Induction or repression or synthesis of enzyme. No? When you talk about induction, you are going down the level of genetic mechanism. Like if there is increase in insulin as in the developed state, this will increase the synthesis of key enzymes involved in glucose degradation. And of course, if you have increased glucagon as occurs in starvation, this will increase the synthesis of enzymes involved in glucose synthesis. Now. So this is genetic level of control, induction or repression of enzyme synthesis no, through genetic manipulation. These are just common patterns of metabolic pathways. Just go over this. No? Okay. I think Santos Elvira, will you try to answer this? Elvira Santos.
Which type of regulation is present upon phosphorylation of the enzyme? A. Allosteric control. B. Covalent modification. C. Enzyme induction. D. Feedback regulation. My answer po is letter B. Covalent modification.
Good. Ibig sabihin, hindi ka pagutom, no? Okay. Sino susunod? Saroka, Josephine? Josephine Saroka.
Hello po.
Yeah, go ahead.
In the presence of hypercholesterolemia, which of the following regulatory controls will attempt to reduce the abnormal level? A.
Okay.
Allosteric modification. B. Covalent modification. C. Feedback inhibition. D. Zymogen activation. Letter B po.
Gutom ka na talaga. Hindi ka na makapag-isip. Ano?
C po, Doc. Feedback inhibition.
That's correct. Feedback inhibition. Okay. Okay. I think this is the last slide affecting enzyme. There are 7 factors affecting temperature, pH, substrate, concentration, cofactors. No? Okay, mabilis na lang ito. Okay, temperature, effect of temperature on enzyme activity. This is the temperature activity profile of an enzyme. On the x-axis, you plot temperature, increasing temperature. On the y-axis, you plot velocity. All right. Here, as you increase temperature, the velocity increases until the optimum temperature is reached. Optimum temperature would be the temperature at which you have maximal velocity. Beyond the optimum temperature, there will be rapid drop in velocity because heat inactivation or denaturation of the enzyme. Remember, enzymes are made up of amino acids or proteins, and therefore, heat denatures your proteins, there will be sudden decrease in velocity after the optimum temp. Before, you have increasing enzyme activity. Why? Because of increased kinetic energy, energy of motion. It is increased collision between the enzyme and the substrate, and therefore you have increased velocity. Before the optimum, but beyond the optimum, there will be rapid decrease in velocity because of denaturation of the enzyme. Okay? So may mga enzyme na may specific optimum temperature. Meaning, yung iba mataas ang kanilang optimum, yung iba mababa. I think most human enzymes have optimum temperature something like 50 to 60 degrees centigrade. No? That would be effect of temperature on velocity. pH naman, okay, I'm sorry for that. Okay, take note that you have a curve. Curve is skewed to the right. Naka-skewed to the right. Insofar as pH, you have a bell-shaped curve. You see a bell shape here. Mukhang bell ito. So sa x-axis, you plot pH. On the y-axis, you have velocity. And this is the optimum pH. Before and beyond optimum pH, there will be decreased velocity. Gets nyo yun? Before and beyond optimist decreased velocity. Optimum pH, ibig sabihin, velocity will be maximum. And this is explained on the basis of the ionization of the amino acids lining up the active site of the enzyme before and beyond optimum pH of that particular enzyme. So a bell-shaped curve will be what? Found here. All right. Ito, there are several enzymes that have varying optimum pH. Pepsin, di ba galing yun sa stomach? Ang stomach more on the acidic side. Optimum pH niya would be something like 1 or 2. Trypsin, something like 6. Okay, optimum pH. Alkaline phosphatase is found in your intestine. Intestine medyo alkaline sadya. And therefore the optimum pH something like would be 8 to 9. So there are different enzymes in the body with optimum pH depending on their sites or where you find them. Okay? Effect of chlorides, bromides, these are cofactors, no? And we have learned that cofactors what increase the rate of enzyme catalysis because certain enzymes need the presence of your cofactors: zinc, manganese, iodide, bromide, potassium, magnesium. Okay. And finally, effect of substrate concentration. Effect of substrate concentration. Again, for a limited amount of enzyme, the velocity of the reaction increases as substrate concentration increases until you reach the Vmax here. So once you reach the Vmax, there will be no effect on the maximal velocity because by this time, all the enzymes and substrate have been filled up by your substrate. Clear? We know that. But here, you have a decline in your velocity. Some books will tell you there is a decline with further increases of your substrate concentration. And I find this, absurd kasi we have learned all along that at Vmax, kahit nataasan mo yung substrate, hindi na magbabago yung velocity because all of the enzymes have been saturated. And here, some authors would like to say that even with increasing substrate concentration, the Vmax will be affected bababa. So palagay nyo bakit? Bakit bumababa dito? Eh samantalang dapat Vmax pa rin. All right. Let me see. Joy and Sebastian. Anyone guess here? Joy and Sebastian, are you here? Hmm?
Hello, Doc.
Yes.
Ano po yung question ulit? Sorry.
Dito sabi ko, 'di ba dapat 'pag Vmax ka, wala nang effect sa velocity kasi all the enzymes have been touched by the substrate and therefore further increase in substrate concentration will no longer affect your Vmax. Talagang Vmax pa rin. Pero dito, pinapakat nila, 'pag nag-increase ka ng substrate, ang velocity mo bababa. Bakit kaya? Hmm? Wow. Kahit na sino. Hmm? Kahit na
Doc, kasi
yeah.
marami na pong substrates ang meron, tas
No,
nabablock na
no,
po
no,
yung active
no.
po.
What?
Marami na pong substrates ang present. Tapos, nangyayari po is nabablock po nila yung active sites. Kaya, bumababa po yung Vmax.
Oh. Ibig sabihin, ang dami-daming substrate pero wala nang enzyme. It could be. It could be, no? Or it could be possible that ang dami-daming enzyme or substrate, they're fighting each other for the enzyme. Nagpa-fight sila hanggang sa nakalimutan nila yung enzyme na. Eh di bababa yung kanyang velocity. But this is rather absurd, no? So in reality, we accept the fact that at Vmax there should be no longer effect on velocity because the velocity has reached a maximum. Clear? Okay, I think okay. Sino pa dito? Can I go back to sino ang hindi nakapag-rehead kanina? Tia Marie Baay. Will you try to answer this, Baay?
The pH activity profile of enzyme in general demonstrate which of the following curves: A, bell shape; B, hyperbolic; C, linear flat; D, sigmoid. Answer po is A.
Okay, bell shape. That's correct. Okay. Next, Nathan Kalayag. Will you answer this? Nathan? Ay. Anong answer mo, Nathan? Okay, that's correct. Ionization of the enzyme. Okay. Castro, Princess Darlimple.
Yes po.
Will you read the question?
What is the effect of temperature beyond the optimum on enzyme activity? A. Denaturization of the enzyme. B. Ionization of the coenzyme. C. Ionization of the enzyme. D. Substrate binding. A po, denaturization of the enzyme.
Denaturation, hindi denaturization. It should be
Sorry
denaturation.
ba? Sorry.
All right. It will be denaturation of the enzyme. Okay, yan. Let me have Chavez, Nicole, Mike Carey.
Choose the correct curve, type of enzyme or enzyme activity factor pair. Letter C po, sigmoid curve allosteric enzyme.
Ganun ba yun? Bell shape temperature, mali, di ba? Dapat ano yan, pH. Linear curve, non-allosteric enzyme. Sigmoid. Oh, allosteric enzyme. So your answer is letter C?
Yes po. Yes po.
Correct. Okay. Sige. Sumunod si Lisette Cruz. Will you answer this, Lisette Cruz?
An increase in temperature before the optimum temperature for the given enzyme increases the reaction velocity due to increased A. Concentration of the enzyme, B. Concentration of the substrate, C. Ionization of amino acid in the active site of the enzyme, D. Kinetic energy of enzyme and substrate.
What's your answer?
Mm, D po.
D as in dog or B as in boy?
D as in dog po.
Okay. So kinetic, that's correct. Oh, enzymes in the okay. Normally, ang enzyme natin nasa loob ng nasa loob ng ng kuwan natin, ng plasma, enzyme. Nandun sa intravascular system natin, okay? Now, in the presence of necrosis or disease or trauma, hmm? I'm sorry. Normally, ang mga enzyme natin nasa cells. Okay, let me correct myself. Inside the cells, no? In the presence of trauma, disease, or necrosis, these enzymes are brought to the blood, correct? And therefore, measurement of the amount of enzymes in the blood, okay, becomes marker for diseases. Correct? Yun ang ibig sabihin ng kwan. Like, for example, I had told you earlier, yung troponin is found only in your cardiac muscles. O Castro, huwag mo kaming tulugan. Humihikab ka pa. Palagay ko nag-aral kang maigi sa exam, kaya inaantok. Alright? Saan? Okay. Troponin is found exclusively in cardiac muscle. Okay? Kaya pag may MI ka, yung troponin na yun, nag escape pupunta sa blood. And therefore, a patient with MI, you get troponin. Pag mataas yun, then you have a diagnosis of MI. That's ibig sabihin ng there are certain enzymes that are markers for diseases. Okay? Alkaline phosphatase is GPT, is GOT. These are markers for liver diseases. Isn't it? Okay. Prostatic surface antigen is found in your prostate gland. Isn't it? Kaya pag mataas ang level ng PSA sa blood, it tells you that the patient most likely have prostatic cancer. Sabihin nun. At ito yung sinasabing cardiac changes. No? Dati ginagamit ang lactate dehydrogenase, creatine kinase, aspartate aminotransferase as markers for diseases, for cardiac problems. However, itong mga enzyme, itong mga yan, itong tatlo, they're also found in other tissues. And therefore, these are not specific for, cardiac problems. Troponin is again found only in your cardiac muscles. And therefore, if you measure the level of this in the blood, all right, at tapos mataas, it tells you that the patient has MI. Pag hindi mataas, ibig sabihin hindi MI yon. And take note that troponin here, ito yon, troponin, peak level niya would be on day 1 of your illness. Sinet? Tapos bababa sa normal level on day 14. All right? So if a patient comes to you on day 6, buhay siya, sabi niya, Doc, I had MI. Tama? Will you order for measurement of troponin in the blood? knowing your temporal profile of your troponin. Oh, let me repeat. O kaya, let's say, day 10, nagpunta sa'yo, buhay siya, Doc, nagkaroon ako ng MI. MI kaya yon? Sige, tignan natin. Will you order for troponin? Measurement? Ano sa palagay nyo? Disena. Ay, meron bang disena? I'm sorry. SP na pala.
Hindi na po kasi pababa na po yung levels ng troponin.
Yeah, mababa na yung level eh. Sinet, mababa na. Di wala ka na makukuha diagnostic parameter. Pag kinuha mo on the first day, yan, mataas. You can make a diagnosis. Alright? So, temporal of cardiac enzymes with MI. I think these are my summary. Okay. Oh, yan. Last question. What is the difference between a first-year medical student and an enzyme? Okay. Okay. These are my references. So thank you very much for listening. It has been a long Friday morning. Alauna na tayo. You have a class after this? Wala, no? May klase kayo? Wala.
Magka-class po ba si Doc?
Ha?
Doc, yung schedule po is platelets pero
Ano?
yung topic po dapat is discussion about sa ano, yung kay Doc Lego po sana.
Ano ba yung discuss nyo dapat?
Wait lang po Doc, double check lang. Platelets po at
Gusto niyang kwan. Okay, sige. So, yung kanyang discussion on platelet and blood coagulation, sasabi sa introduction to metabolism, di ba? Okay, sige, sige. So, any questions about enzymology? Mahirap ba intindihin? Sabi ni Feo, hindi daw. Okay, good. All right. So, thank you for listening and thank you for participating in the question and answer part. No? So, enjoy your weekend.
Thank you, Doc. Happy lunch.
lahat, lahat tayo gutom.